There's something awe-inspiring about staring up at the night sky filled with countless stars, galaxies, and the vast, silent darkness stretching beyond what our eyes can see. But what if I told you that hidden within that darkness lies a cosmic secret, a mysterious glow that shouldn't be there? This isn't science fiction, it's real. Scientists call it the cosmic infrared background, or CIB for short, and it's one of the most baffling puzzles in modern astronomy. Imagine peeling back the layers of the universe like an onion, only to find a faint, unexplained light that defies everything we thought we knew about how space works. This glow isn't coming from stars, galaxies, or even distant quasars. It's something else entirely, an enigma woven into the very fabric of the cosmos. And here's where it gets even stranger. Scattered across this infrared backdrop are 40 anomalies, irregularities so peculiar they've left even the brightest astrophysicists scratching their heads. Some of these anomalies appear too bright, others too dim. Some cluster in ways that shouldn't be possible, while others vanish without a trace. Each one is a cosmic riddle, whispering clues about gaps in our understanding of the universe's history, structure, and even its fate. What could be causing these glitches in the infrared sky? Are they echoes of long-dead stars, traces of undiscovered physics, or something even more extraordinary? The truth is, we don't have all the answers yet, but that's what makes this journey so thrilling. Over the course of this video, we'll explore these 40 cosmic oddities one by one, diving into the theories, the debates, and the mind-bending possibilities they represent. By the end, you might just see the night sky a little differently, not just as a static backdrop, but as a living, shifting mystery waiting to be solved. So, are you ready to step into the unknown? Let's begin. The first anomaly in our cosmic detective story begins with a faint, ghostly light, an infrared glow that blankets the sky like an invisible veil. Astronomers first noticed this mysterious signal when they pointed their telescopes beyond the familiar stars and galaxies, expecting to find darkness. Instead, they detected a diffuse, almost ethereal radiance, like the universe itself was humming a tune we couldn't quite decipher. This glow, known as the Unidentified Infrared Background, was discovered in the late 1990s by space telescopes designed to study the universe in infrared light. At first, scientists assumed it must be coming from known sources, distant galaxies, newborn stars, or even dust warmed by starlight. But when they added up all the expected contributions, something didn't fit. The glow was too bright, too uniform, and too persistent to be explained by conventional astrophysics. It was as if the cosmos had left all the lights on and no one could find the switch. So what could be causing it? One leading theory points to primordial stars, enormous, ancient giants that burned hot and died young in the universe's infancy. These first-generation stars, made purely of hydrogen and helium, would have emitted vast amounts of infrared radiation as they collapsed into black holes or exploded in supernova. Their light, stretched by the expansion of the universe over billions of years, might now reach us as this diffuse glow. But there's a catch. Even if these early stars existed, their combined output shouldn't match the intensity we're seeing. Which raises another possibility. Could this glow be evidence of something even more exotic, like decaying dark matter particles or collisions in hidden dimensions? Some theorists suggest that undiscovered physics might be at play, processes so alien to our current models that they rewrite the rules of cosmic evolution. Yet for every tantalizing hypothesis, there's a frustrating dead end. The more we study this infrared enigma, the more it resists easy explanation. It's a reminder that the universe often keeps its most profound secrets just beyond our grasp, waiting for the next breakthrough or the next curious mind to shine a light into the darkness. Just when we thought the infrared mysteries couldn't get any stranger, astronomers stumbled upon another head-scratcher, an inexplicable spike of light at precisely 3.5 microns. Picture this, you're scanning the cosmos, sifting through wavelengths like a cosmic radio dial, when suddenly, one frequency blares louder than the rest. That's exactly what happened when telescopes like NASA's Spitzer Space Telescope detected this odd excess emission, a spectral fingerprint with no obvious cosmic culprit. At first glance, the explanation seems straightforward. Interstellar dust warmed by starlight often glows in infrared, but this particular signal doesn't match the patterns of ordinary dust. It's too intense, too focused. One hypothesis points to the remnants of the universe's very first stars, colossal behemoths hundreds of times more massive than our Sun. These primordial giants would have burned furiously and died young, scattering heavy elements and leaving behind a distinct infrared signature. If their ashes are still drifting through space, they might account for this anomalous glow. But here's where things take a turn. Some researchers argue that even these ancient stars couldn't produce such a sharp spike. That's led to more radical ideas like the possibility of exotic particles decaying in deep space. Certain theories of dark matter suggest it could slowly break down, releasing energy at specific wavelengths. 3.5 microns might just be the calling card of a ghostly particle we've yet to detect directly. The plot thickens when you consider alternative explanations, like hidden populations of rogue planets or failed stars known as brown dwarfs. These cold, dim objects emit mostly infrared light, and if enough of them lurked unseen in the cosmic shadows, they could theoretically contribute to the excess. Yet, surveys haven't found nearly enough to explain the signal's strength. What makes this anomaly so tantalizing is how it refuses to fit neatly into any single box. It's a cosmic koan, a riddle that challenges our assumptions about what's out there. Whether it's the echo of the first stars, the whisper of dark matter, or something entirely unforeseen, this 3.5 micron mystery proves that even in the quietest corners of the universe, there are still stories waiting to be told. Among these cosmic riddles, one stands out for its sheer defiance of expectations: the case of the missing galactic light. Imagine calculating every known star, every swirl of interstellar dust, every flicker of energy from distant galaxies, only to realize the numbers don't add up. The universe, it seems, is playing a game of hide and seek with its own light. When astronomers tally up the infrared emissions from all observed galaxies, they find a glaring shortfall. Based on our best models, there should be more light, far more. It's as if entire galaxies are flickering in and out of existence, their energy vanishing into the cosmic void. Where could it be going? One leading suspect is dust, but not just any dust. We're talking about vast, cold clouds of it, so fine and diffuse they're virtually invisible to most telescopes. These stealthy particles could be absorbing starlight and re-emitting it at wavelengths we haven't fully mapped, effectively masking a portion of the universe's glow. Yet even this explanation leaves gaps. If hidden dust were the culprit, we'd expect to see certain telltale patterns in the infrared spectrum, specific signatures of heat and composition. Instead, the missing light behaves more like a shadow puppet, leaving clues that don't quite match any known material. That's led some scientists to propose even wilder ideas. Could there be entire populations of ultra-faint galaxies lurking just beyond our detection, their light too dim for current telescopes to catch? Or might the missing energy be tied to something more exotic, like primordial black holes evaporating into the cosmos? Then there's the unsettling possibility that we're not just missing light, we might be missing physics. Some theories suggest that unknown astrophysical processes, perhaps involving dark matter or even quantum fluctuations in the vacuum of space, could be siphoning off energy in ways we've yet to imagine. It's a humbling reminder that for all our advancements, the universe still holds cards close to its chest. What makes this anomaly so gripping isn't just the mystery itself, but what it reveals about how we explore the cosmos. Every discrepancy is a breadcrumb trail pointing toward gaps in our understanding and potentially toward discoveries that could rewrite the textbooks. So the next time you gaze up at the night sky, remember, some of its light isn't lost, it's just waiting to be found. If the cosmic infrared background were a tapestry, it wouldn't hang evenly. Instead, it would ripple with strange, uneven patches of light and shadow. This patchwork, known as anisotropies, might sound like a minor quirk, but it's actually a cosmic time capsule, preserving whispers from the universe's chaotic infancy. Unlike the smooth glow we'd expect from a perfectly uniform early cosmos, these irregularities tell a far more dramatic story, one of clumping matter, gravitational tugs of war, and the seeds of everything we see today. Picture the universe just a few 100 million years after the Big Bang, a seething soup of gas and dark matter, far too hot and dense for stars or galaxies to exist. Yet somehow, within that primordial fog, tiny fluctuations in density began to emerge. These minuscule ripples, no larger than 1 part in 100,000, were the cosmic blueprints for all future structure. Gravity amplified them over eons, pulling matter into denser knots that eventually collapsed into the first stars and galaxies. And here's where the infrared background's anisotropies come in. They're the faint afterglow of that very process frozen in time. What's baffling is how lumpy these patterns are. When scientists map the infrared sky, they don't see gentle gradients, they find sharp edges, unexpected voids, and clusters that defy predictions. Some regions glow brighter than entire galaxy clusters should account for, while others appear suspiciously dark, as if something's blocking or absorbing the light. One theory suggests these anomalies trace back to the first supermassive black holes, which may have voraciously consumed surrounding gas, heating it to extreme temperatures and flooding their corners of the universe with infrared radiation. Others propose that vast, unseen webs of dark matter funneled primordial gas into concentrated pockets, creating hotspots of star formation that burned briefly but intensely before vanishing. But perhaps the most tantalizing clue lies in what these anisotropies don't match. When astronomers compare them to the cosmic microwave background, the even older relic light from the Big Bang itself, the patterns don't align as neatly as models predicted. It's like comparing a sketch to the final painting and finding strokes that don't belong. This discrepancy hints at forces we haven't accounted for, perhaps new physics governing how matter behaved in those first critical epochs. Could dark energy have played a role earlier than we thought? Might there have been exotic particles influencing gravity's grip on the infant universe? The anisotropies don't answer these questions yet. They simply remind us that the universe's childhood was far more turbulent than we imagined. What makes these infrared wrinkles so extraordinary isn't just their existence, it's their refusal to fit neatly into our cosmic narrative. They're the cracks in the foundation, the places where the universe whispers, there's more to the story. And as telescopes grow sharper, these subtle irregularities may finally reveal how the void gave birth to everything we know. Deep in the cosmic shadows, astronomers have begun hunting for ghostly giants, stars so ancient and alien they might rewrite the story of the universe's dawn. These aren't the blazing suns we know today. They're something far stranger, dark stars, not dead husks like black holes or neutron stars, but living, glowing behemoths powered by an entirely different kind of fire. According to one daring theory, these elusive objects could be the key to unlocking several of the infrared background's most persistent mysteries. The idea hinges on the universe's first chapter, a time before galaxies, before even the first conventional stars ignited. In that primordial darkness, vast clouds of hydrogen and helium slowly collapsed under gravity's pull. But here's the twist. If dark matter, the invisible glue holding galaxies together, was concentrated in those early clouds, it might have triggered an exotic form of stellar birth. Unlike modern stars fueled by nuclear fusion, dark stars would rely on annihilating dark matter particles at their cores, releasing energy in a slow, steady burn. The result, stars hundreds of times larger than our Sun, glowing not with fierce blue-white light, but with an eerie, diffuse infrared radiance. If they existed, these shadowy giants would leave behind distinct fingerprints in the cosmic infrared background. Their light, stretched by billions of years of cosmic expansion, would manifest as subtle excesses at specific wavelengths, exactly the kind of anomalies we've detected. Even their deaths would be peculiar. Instead of exploding as supernova, they'd collapse directly into black holes, seeding the early universe with the gravitational anchors around which galaxies later formed. But finding proof is like searching for cosmic needles in a haystack the size of the universe. Dark stars would be incredibly faint by now, their light diluted across incomprehensible distances. Current telescopes might only catch them if they formed in dense clusters, amplifying their combined glow. Even then, distinguishing them from ordinary distant galaxies requires painstaking analysis of their spectral signatures, hunting for telltale dips or bumps in the infrared light that betray their dark matter engines. Some researchers argue we've already glimpsed hints. Certain unexplained infrared sources, unusually red and extended, match simulations of what dark stars might look like today. Others remain skeptical, pointing out that alternative explanations, like dust-obscured galaxies or rare stellar mergers, could mimic these signals. The debate thrives because the stakes are so high. Confirming dark stars wouldn't just solve an infrared puzzle, it would prove dark matter can interact in ways we've never seen, opening a new window into the universe's hidden architecture. What makes this hypothesis so captivating is its audacity. It dares to imagine a cosmos where the first light didn't come from fire as we know it, but from something far more mysterious. Whether dark stars flicker in the data or fade into legend, their story reminds us that the universe's infancy might have been stranger than we ever dreamed. Zooming in on the cosmic infrared background reveals something startling. Tiny, flickering patches of brightness that defy explanation. These aren't the grand, sweeping anisotropies we've discussed before. These fluctuations are far smaller, more erratic, like fireflies blinking in a vast cosmic meadow. At first glance, they might seem insignificant, but their existence hints at processes so dramatic they could reshape our understanding of the universe's earliest epochs. The mystery lies in their scale. Conventional astrophysics predicts that the infrared background should smooth out when we examine it at fine resolution, like waves dissolving into foam. Instead, we see sharp, pixelated variations, bright spots, and dim voids no larger than a few arcminutes across. These fluctuations are too pronounced to be caused by ordinary galaxies or dust clouds. So what's creating them? One compelling explanation points to the universe's first black holes, voracious monsters born from the collapse of primordial gas clouds or the death of those hypothetical dark stars. As these black holes devoured surrounding matter, they would have unleashed torrents of energy, lighting up their corners of space like cosmic lighthouses. Their brief, violent lives could have left behind these infrared imprints, fossilized in the background glow. But there's a twist. The patterns don't quite match what simulations predict for early black holes. Some regions flicker more intensely than expected, while others are eerily quiet. That discrepancy has led researchers to consider an even more exotic culprit, clumps of dark matter annihilating itself. Certain theories suggest that dark matter particles, when densely packed, might collide and annihilate, releasing bursts of energy including infrared light. If true, these flickering patches could be the first indirect glimpse of dark matter's hidden interactions, a shadowy dance playing out across the cosmos. Yet the plot thickens when we consider alternative explanations. Could these fluctuations be relics of cosmic strings, hypothetical defects in spacetime left over from the Big Bang? Or might they trace back to quantum fluctuations in the infant universe, amplified by unknown physics into detectable infrared signatures. Each possibility carries profound implications, but none yet fit the data perfectly. That's the maddening beauty of these small-scale anomalies. They refuse to settle into a single narrative. What makes these fluctuations so tantalizing isn't just their defiance of expectations, but their potential to bridge gaps in cosmic history. They might hold clues about how the first black holes seeded galaxy formation, or how dark matter shaped the universe's large-scale structure. For now, they remain cosmic breadcrumbs, leading us deeper into the labyrinth of the unknown. And as telescopes grow more sensitive, these subtle flickers may finally reveal whether we're seeing the fingerprints of black holes, dark matter, or something even more extraordinary. Among the infrared background's many riddles, one wavelength stands out like a sore thumb: 24 microns. At this specific frequency, the cosmos emits far more radiation than our models predict, creating a glaring excess that defies easy explanation. Think of it like tuning into a radio station and hearing static where there should be silence. That unexplained noise, it's the universe broadcasting a signal we're still struggling to decode. The leading suspects in this cosmic mystery are polycyclic aromatic hydrocarbons, or PAHs for short. These aren't your everyday dust particles, they're sprawling, carbon-based molecules, often described as the soot of the universe. Formed in the winds of dying stars and scattered across interstellar space, PAHs absorb ultraviolet light and re-emit it at infrared wavelengths, including the telltale 24-micron band. If they're abundant enough, they could theoretically account for the excess. But here's the catch: the scale of the surplus suggests there's more PAHs out there than our current star formation and stellar death rates can explain. It's like finding a city's worth of fingerprints at a crime scene, but only enough people to account for a small town. That discrepancy has sent scientists scrambling for alternative explanations. One intriguing possibility involves nanoparticles of silicate dust, tiny mineral fragments that could also glow at this wavelength under the right conditions. Another theory points to quantum dots, microscopic crystalline structures that emit light when energized. These speculative ideas stretch our understanding of cosmic chemistry, hinting at processes we've yet to observe directly. But the plot takes an even wilder turn when we consider non-material explanations. Some researchers have floated the idea that this excess could be tied to the decay of hypothetical particles like actions, a leading candidate for dark matter. If these ghostly particles were breaking down in space, they might release energy at precise wavelengths, including 24 microns. It's a long shot, but in the absence of definitive answers, even fringe theories get a seat at the table. What makes this anomaly so compelling is how it bridges the familiar and the fantastical. On one hand, it might just be cosmic soot, the mundane remnants of stellar life cycles. On the other, it could be a clue to something far grander, a fingerprint of invisible matter or a window into quantum processes playing out on galactic scales. Until we uncover more evidence, the 24-micron excess remains a tantalizing reminder that sometimes the universe's quietest signals shout the loudest questions. The universe has a habit of leaving cryptic signatures, and none are more intriguing than the unexpected handshake between two cosmic backgrounds separated by billions of years. On one side, there's the cosmic infrared background, the faint glow of ancient starlight stretched by time. On the other, the cosmic microwave background, the relic radiation from the Big Bang itself. At first glance, these two should be strangers, one born from the fiery dawn of the cosmos, the other from the slow simmer of stars that came much later. Yet when scientists compared their patterns, they found eerie similarities, as if the universe had stitched them together with invisible thread. This phenomenon, called the CIBCMB cross-correlation, reveals patches where the infrared glow and microwave ripples align more closely than chance should allow. It's as if someone took a fingerprint from the universe's infancy and pressed it onto the later tapestry of stars and galaxies. At the heart of the mystery is a question: how could events so far apart in time, separated by billions of years, leave matching imprints? One promising explanation lies in the gravitational dance of dark matter. Imagine the early universe as a canvas splattered with tiny density variations, the seeds of future galaxies. As these regions grew, their gravity bent the paths of photons from the CMB, subtly distorting its pattern. Later, when the first stars ignited, their infrared light traced the same underlying dark matter scaffolding, creating echoes of that ancient distortion. In other words, both backgrounds might be different reflections of the same cosmic skeleton, but skeptics point out gaps in this elegant story. Some alignments appear too strong, too precise, as if amplified by forces we haven't accounted for. Could there be unknown particles influencing gravity's pull during those critical early epochs? Or might primordial magnetic fields threading through space like invisible wires have shaped both backgrounds in tandem? Then there's the radical fringe. Theories suggesting these correlations hint at something deeper, an undiscovered symmetry in the laws of physics that binds cosmic epochs together. If true, this wouldn't just solve an infrared anomaly, it could rewrite our understanding of causality itself. What makes this cross-correlation so compelling isn't just the puzzle it presents, but the way it forces us to see the universe as an interconnected whole. The past isn't just prologue, it's a living layer of the cosmos whispering to us through the faintest of signals. And in those whispers, we might just find the key to unraveling everything. Even in the darkest reaches of space, light can play tricks on us, and nowhere is that more apparent than in the heated debate over the zodiacal light. This faint, ethereal glow, sometimes visible from Earth as a pyramid of radiance stretching up from the horizon just before dawn or after dusk, comes from sunlight scattering off trillions of dust grains in our own solar system. For centuries, it was considered little more than a celestial curiosity, but when astronomers began studying the cosmic infrared background, this local phenomenon suddenly became a cosmic suspect. Could the zodiacal light be masquerading as something far more profound, contaminating our measurements of the ancient universe? The controversy hinges on a simple but maddening problem: subtraction. To isolate the true cosmological signal of the CIB, scientists must first account for and remove all foreground interference, including the zodiacal dust's contribution. But here's where things get messy. Models of solar system dust distribution rely on complex assumptions about particle sizes, compositions, and orbits. Even slight errors in these assumptions can leave behind artificial anomalies in the cleaned-up data ghost signals that don't belong to the distant universe at all. Some researchers argue that certain infrared excesses, especially those at shorter wavelengths, might not be cosmic fingerprints but rather the lingering echoes of imperfect dust subtraction. Critics of this view counter with compelling evidence. If zodiacal contamination were the culprit, we'd expect the anomalies to correlate strongly with the ecliptic plane, where solar system dust is densest. Yet many puzzling signals appear uniformly across the sky, defying this pattern. There's also the matter of spectral signatures. The light from zodiacal dust has distinct wavelength dependencies that don't always match the CIB anomalies. Still, the disagreement isn't just academic, it cuts to the heart of how we interpret the universe's early history. If some infrared clues turn out to be solar system noise, entire theories about primordial stars or dark matter decay could need rethinking. The debate took an unexpected turn when new data from the James Webb Space Telescope complicated the picture further. Its unprecedented sensitivity revealed intricate structures in the zodiacal dust cloud, including previously unseen filaments and voids that standard models hadn't predicted. Suddenly, the task of cleaning up this foreground light became even thornier, like trying to erase a shadow while the object casting it keeps moving. What makes this anomaly so uniquely frustrating is that it forces us to confront the limits of our own cosmic backyard. Before we can peer into the universe's infancy, we must first reckon with the dust at our feet, or rather, floating between our planet and the stars. Whether these infrared mysteries are cosmological revelations or mere reflections of local clutter, one thing is certain. The zodiacal light debate proves that sometimes the hardest thing to see clearly isn't the distant unknown, but the familiar haze right in front of us. Most of the cosmic infrared background glows steadily, like the embers of a fading fire. But scattered across this backdrop are enigmatic flickers, objects that brighten, dim, or vanish entirely over timescales ranging from days to decades. These aren't ordinary variable stars or distant supernovae. They're something far harder to pin down, rogue signals that defy classification, blinking in and out of the infrared sky like cosmic Morse code we can't yet decipher. Take one puzzling example documented by the Spitzer Space Telescope, a faint source that flared to 20 times its original brightness in just under a year, then faded back into obscurity. No known stellar outburst matches its profile. It wasn't hot enough to be a supernova, nor did it show the telltale signatures of a merging black hole pair. Even more bizarrely, its spectrum lacked the chemical fingerprints of typical cosmic cataclysms. It was, in essence, a celestial ghost, an event with no clear astrophysical identity. Theories about these transient infrared anomalies range from the speculative to the revolutionary. One camp suggests they could be tidal disruption events, occasions where a star strayed too close to a black hole and was shredded into a glowing debris stream. But most such events emit copious X-rays, which these flickers lack. Another possibility involves failed supernova, where massive stars collapse directly into black holes without the usual explosive finale. The result might be a brief infrared burst as surrounding dust absorbs the dying star's final whispers of light. Then there's the wildcard explanation: extraterrestrial megastructures. While highly improbable, some have floated the idea that advanced civilizations could build vast energy-harvesting arrays around stars, whose intermittent operations might produce irregular infrared flares. It's a fringe hypothesis, but the sheer strangeness of these signals keeps even the most unconventional ideas on the table. What makes these time-variable sources so tantalizing isn't just their mystery. It's their potential to reveal entirely new astrophysical processes. Every unexplained flicker could be the first hint of phenomena we've never imagined, lurking in the gaps of our understanding. And as observatories grow more adept at monitoring the infrared sky, we might finally catch these cosmic will-o'-the-wisps in the act, revealing secrets they've held for billions of years. One of the most persistent puzzles in modern cosmology revolves around a special class of ancient galaxies, those that formed when the universe was still in its infancy. These galaxies, known as Lyman break galaxies, act like cosmic time capsules, allowing us to peer back into an era when the first stars and galaxies were just beginning to illuminate the darkness. But here's the catch: when we measure their infrared light against theoretical predictions, something doesn't add up. The numbers fall short, sometimes dramatically. It's as if these galaxies are holding back part of their glow, keeping secrets from us across billions of light years. The discrepancy stems from an elegant technique astronomers use to detect these distant giants. Lyman break galaxies get their name from a distinctive feature in their ultraviolet light spectra, a sharp drop-off caused by hydrogen gas absorbing shorter wavelengths. By identifying this break, scientists can estimate their distance, age, and luminosity. And based on these properties, we can calculate how much infrared light their stars and dust should emit as that energy gets stretched by cosmic expansion. Yet time and again, observations reveal far less infrared light than expected. Some estimates suggest the deficit could be as much as 60%. Where is all that missing energy? One possibility is that these early galaxies weren't as dusty as we assume. Dust plays a crucial role in absorbing starlight and re-emitting it at infrared wavelengths. So if these galaxies lacked substantial dust clouds, their infrared output would naturally be fainter. But that raises new questions. Why would the universe's earliest galaxies be so dust-poor when later generations weren't? Another explanation points to the nature of the stars themselves. The first stars were likely hotter, bluer, and more massive than those forming today, producing intense ultraviolet radiation but less of the longer wavelength light that eventually redshifts into the infrared. If these galaxies were dominated by such stars, their spectral energy distributions would look fundamentally different from modern galaxies, potentially throwing off our predictions. Then there's the wildcard factor: escape. Some theorists argue that in these young, chaotic galaxies, a significant fraction of starlight might have simply leaked out unimpeded, avoiding absorption by dust altogether. The early universe was more transparent, with fewer heavy elements to block light, meaning photons could travel farther before being scattered or absorbed. If true, this would mean we're underestimating just how much raw starlight these galaxies actually produced. Of course, there's always the chance our models are missing something deeper. Could there be unknown astrophysical processes at work in these primordial environments, something that alters how light is emitted or absorbed? Or might the very structure of space-time have been different at such early epochs, subtly skewing our observations? The Lyman break discrepancy isn't just a numerical oddity, it's a challenge to our understanding of cosmic dawn, a reminder that the universe's first chapters still hold surprises waiting to be uncovered. What makes this anomaly so compelling is how it forces us to rethink the basics. These galaxies aren't just faint dots in a telescope's eyepiece, they're the building blocks of everything we see today. If our assumptions about their light are off, it could mean revising entire chapters of cosmic history, from star formation rates to the timeline of galaxy assembly. Until we solve the riddle of their missing infrared glow, we're left peering through a keyhole, catching only glimpses of the universe's earliest, most transformative era. Hidden in the depths of cosmic time, before galaxies took shape and stars filled the void, the universe might have been crawling with tiny, voracious monsters, primordial black holes. These aren't the stellar mass black holes we know today, forged in the collapse of massive stars. These would have been born in the chaos of the Big Bang itself, from dense quantum fluctuations so extreme they pinched off into microscopic singularities. Some could have been as small as a proton, others as massive as a mountain, and if they exist, their fingerprints might be all over the cosmic infrared background, whispering secrets from the universe's first moments. The connection hinges on two key processes: Hawking radiation and accretion. Let's start with Hawking radiation, the eerie quantum phenomenon where black holes slowly evaporate by emitting particles. The smaller the black hole, the faster it radiates, and for primordial black holes born near the lower end of the mass scale, this evaporation would have been explosive. In their final moments, they'd unleash torrents of high-energy photons, which over billions of years would redshift into the infrared. If enough of these tiny black holes popped like cosmic firecrackers in the early universe, their collective afterglow could contribute to the CIB's unexplained patches of brightness. Then there's accretion, the process of black holes devouring surrounding matter. Larger primordial black holes, those that survive to the present day, would have spent eons pulling in gas and dust from their environments. As this material spirals inward, friction heats it to incredible temperatures, causing it to glow. While most of this emission would be in X-rays or visible light, the dustier reaches of these feeding zones would absorb and re-radiate energy at infrared wavelengths. If primordial black holes are scattered throughout the cosmos, their accretion disks could be adding subtle, diffuse infrared light to the background. But here's where things get thorny. The math doesn't quite line up, at least not yet. For Hawking radiation to explain significant CIB anomalies, there would need to have been an overwhelming number of tiny primordial black holes, so many that their evaporation should have left other, more obvious traces in the cosmic microwave background or gamma-ray sky. Similarly, accretion from larger primordial black holes would require them to be both abundant and actively feeding, a scenario that might conflict with observations of the modern universe's black hole population. Yet the idea persists because it solves multiple puzzles at once. Primordial black holes could simultaneously account for certain infrared excesses and serve as candidates for dark matter, killing two cosmic mysteries with one stone. Some models even suggest they could have seeded the formation of the first stars and galaxies, adding another layer to their potential influence on the infrared background. What keeps this hypothesis alive is its sheer versatility. Unlike more conventional explanations, primordial black holes offer a way to bridge gaps in our understanding of everything from particle physics to galactic evolution. They're cosmic wildcards capable of turning up in unexpected places and leaving behind just the kind of subtle, perplexing signals we see in the CIB. Until we either find definitive proof of their existence or rule them out entirely, they'll remain one of the most tantalizing and contentious pieces of the infrared puzzle. Buried in the infrared sky lies an odd spectral bump at 1.4 microns, a peculiar excess of light that shouldn't exist. Scientists call it the CIB hump, and unlike the smoother, more predictable parts of the cosmic infrared background, this feature stands out like a sore thumb. It's as if the universe decided to crank up the brightness at this specific wavelength for reasons we're still struggling to understand. The leading suspect behind this anomaly. The universe's very first generation of stars, known as Population 3, these titanic, short-lived behemoths were unlike anything we see today, composed purely of hydrogen and helium, free from the heavier elements that lace modern stars. Theory suggests they burned at extreme temperatures, emitting intense ultraviolet light that, over billions of years of cosmic expansion, would redshift into the infrared, potentially landing right at 1.4 microns. If enough of these stars flared into existence and died young, their collective afterglow could create just such a spectral hump, but there's a problem. Population 3 stars shouldn't have been that common. Current models suggest they were rare, scattered across the early cosmos like isolated bonfires in a vast dark plain. To produce the observed hump, we'd need far more of them than simulations predict, unless these stars were even brighter, hotter, or more efficient at converting mass into light than we've imagined. Alternatively, the hump might hint at something even stranger, an entirely unknown phase of stellar evolution where these primordial giants died in ways we haven't accounted for, releasing bursts of infrared radiation as they collapsed. Then there's the dark horse candidate decaying dark matter. Certain hypothetical particles, like sterile neutrinos or actions, could theoretically decay into photons with energies corresponding to 1.4 microns after accounting for redshift. If true, the CIB hump wouldn't be starlight at all, but the ghostly emission of invisible particles fading out of existence. What makes this anomaly so compelling is its stubborn refusal to fit neatly into any single box. It's a cosmic Rorschach test. Some see the fingerprints of the first stars, others glimpse the shadows of dark matter's demise. Until we peer even deeper into the infrared sky, the hump at 1.4 microns will remain a tantalizing whisper from the universe's dawn, daring us to unravel its secrets. One of the strangest revelations about the cosmic infrared background isn't just what it contains, it's how unevenly that light is distributed across the sky. When astronomers map its glow, they don't find the uniform haze you'd expect from a universe governed by the cosmological principle, the foundational idea that space should look roughly the same in all directions when viewed on large scales. Instead, they discover vast, lopsided structures, regions where the infrared light piles up in great, swirling asymmetries, as if someone tilted the cosmos and let its glow slide to one side. These imbalances aren't small quirks. Some span hundreds of millions of light years, dwarfing even the most colossal superclusters of galaxies. The most famous example, dubbed the infrared dipole, shows a striking excess in one hemisphere of the sky and a corresponding deficit in the opposite direction. It's as if the universe itself is leaning, its infrared light bulbs brighter on one end than the other. This shouldn't happen. According to our standard models, such mammoth irregularities would require forces or conditions so extreme they'd rewrite our understanding of cosmic evolution. So what could be causing these directional oddities? One line of thought points to our own motion through space. Just as a speeding car gathers raindrops on its windshield, Earth's journey through the cosmos might concentrate infrared light in the direction we're heading, an effect called the kinetic dipole. But here's the catch. The infrared dipole's magnitude is several times stronger than what our measured velocity predicts. Either something's amplifying this effect, or there's another, far more exotic driver at work. That's where things get speculative. Some theorists propose these asymmetries could be scars from the universe's birth, relics of primordial quantum fluctuations that got stretched to astronomical scales during inflation. The explosive expansion thought to have shaped the cosmos in its first fractions of a second. If those fluctuations weren't perfectly uniform, they might have imprinted these infrared imbalances like cosmic birthmarks. Others wonder if we're seeing the gravitational echoes of unseen structures beyond our observable horizon, vast concentrations of mass tugging on spacetime so fiercely they skew the infrared light from distances we can't yet probe. Then there's the radical possibility that these asymmetries hint at a fundamental flaw in the cosmological principle itself. What if the universe isn't as homogeneous as we've assumed? What if, on the grandest scales, space has a grain, a preferred direction that breaks the symmetry we've taken for granted? It's a heretical idea, but the infrared background's lopsided glow keeps it alive, whispering that our place in the cosmos might not be as ordinary as we once believed. What makes these large-scale asymmetries so mesmerizing is their defiance. They refuse to fit neatly into our cosmic narratives, challenging not just what we see, but how we frame the universe's very identity. Whether they're artifacts of our motion, relics of creation, or signs of deeper physics, one thing is clear: the infrared sky isn't just a backdrop. It's a mirror reflecting back the cracks in our understanding and the thrilling potential of what we've yet to discover. Galaxies don't float in emptiness, they're cocooned within vast, invisible spheres of dark matter called halos. These halos are the universe's hidden architects, their gravity sculpting galaxies into shape and dictating how they evolve. But when astronomers peered into these cosmic nests, expecting them to glow faintly with the infrared light of ancient stars, they stumbled onto something unsettling. The halos were far darker than theory predicted. Whole swaths of missing light, as if the universe had forgotten to flick the switch. This discrepancy, known as the intrahalo light problem, strikes at the heart of how we think galaxies assemble. According to simulations, as galaxies grow, they cannibalize smaller neighbors, tearing them apart in violent mergers. The shredded stars from these collisions should linger in the halo, adrift in a diffuse cloud that emits a subtle infrared glow. Yet when researchers measured this expected light, they found only a fraction of what models suggested should be there. It's like tracking footprints to a crime scene, only to discover half of them vanish into thin air. One possible explanation cuts to the core of dark matter's mysteries. If dark matter halos are less concentrated or more diffuse than we've assumed, their gravity might not trap wayward stars as effectively, allowing them to escape into intergalactic space. Alternatively, mergers in the early universe might have been gentler, leaving fewer stellar splinters behind. But both ideas raise their own questions. Why would dark matter behave differently on these scales, and how could galactic collisions be too tidy to leave traces? Then there's the wild card. Halo stars might not be as bright as we think. Recent observations suggest some could be incredibly dim, dominated by ancient red dwarfs or even rogue planets too faint to detect. If these dark, cold objects make up most of the intrahalo population, their infrared signatures would be whisper quiet, slipping beneath our telescope's sensitivity. But the most tantalizing possibility is that we're witnessing the limits of galaxy formation itself. Perhaps the models are missing a critical process, something that strips stars from halos or prevents them from settling there in the first place. Whether it's unseen astrophysical forces or gaps in our understanding of dark matter's role, this missing light isn't just an anomaly. It's a clue pointing toward deeper truths about how the cosmos builds its grandest structures and what might still be hiding in the shadows. Scattered across the cosmic infrared background like grains of sand on a dark beach, there's a peculiar population of faint, pinprick sources, tiny dots of light that refuse to resolve into recognizable shapes, no matter how powerfully we magnify them. These aren't the blazing centers of distant galaxies or the telltale signatures of stellar nurseries. They're something far more elusive, unresolved point sources, a ghostly brigade of objects contributing to the CIB's glow without revealing their true identities. And here's the mystery: when astronomers tally up all the known galaxies and stars, they find these unexplained specks account for a stubborn fraction of the infrared sky's light, as if the universe left breadcrumbs leading to a party we weren't invited to. The enigma deepens when we consider just how ancient these objects might be. Many cluster in regions corresponding to the universe's toddler years, a mere few 100 million years after the Big Bang. At such distances, even the most advanced telescopes struggle to distinguish them from noise, their light stretched and dimmed by eons of cosmic expansion. Some could be among the very first star clusters, blazing briefly before vanishing into oblivion. Others might represent primordial black holes, feasting on gas in the darkness before galaxies took shape. There's even a chance there's something entirely unexpected. Exotic stellar objects that defy our current classifications, relics of a time when the laws of physics danced to a slightly different tune. But the real puzzle lies in their collective power. Individually, each point source is vanishingly faint, but together they form a significant portion of the infrared background's unresolved light. It's like listening to a choir where every singer murmurs just below hearing range, yet their combined voices somehow fill the concert hall. This suggests two startling possibilities. First, these objects might be astonishingly numerous, more abundant than all the galaxies we've catalogued combined. Second, their formation mechanisms could be unlike anything we've observed in the modern universe, a lost recipe for building cosmic structures that disappeared as the cosmos matured. The hunt for answers has led to some ingenious detective work. By analyzing the statistical distribution of these point sources, how they cluster or disperse across the sky, researchers have uncovered hints of large-scale patterns. Some groupings align eerily with the cosmic web's filaments, the vast scaffolding of dark matter thought to channel the flow of matter in the early universe. This tantalizes theorists with the notion that we might be glimpsing the seeds of galaxy formation itself, the first flickers of structure emerging from the primordial dark. Yet for every clue, there's a confounding twist. Certain point sources flicker unpredictably, their brightness changing over timescales too rapid for their presumed distances. Others emit spectral signatures that don't match any known celestial object, lacking the chemical fingerprints of stars or quasars. The most radical explanations verge on science fiction. Could some be the remnants of alien megastructures or the wakes of cosmic strings vibrating through space-time? Most scientists dismiss such ideas, but the very fact they're entertained speaks to how deeply puzzling these sources remain. What makes this anomaly so compelling isn't just the mystery of what these objects are, it's what they represent. They're the cosmic equivalent of finding unlabeled fossils in a prehistoric dig, remnants of an era before the universe settled into its familiar rhythms. Whether they're failed galaxies, dark matter factories, or something beyond our current imagination, these unresolved points remind us that the infrared sky isn't just a static image. It's a palimpsest layered with the half-erased stories of the cosmos' wild youth, waiting for the right tools or the right insight to bring them into focus. Among the cosmic infrared background's many quirks, one of the most perplexing is the sudden dip at 2 microns, a wavelength where the expected glow of the universe abruptly dims, as if someone turned down a cosmic dimmer switch. This anomaly, known as the CIB dip, stands out because it defies the smooth curve we'd anticipate from known sources of infrared light. Instead of a steady decline in brightness as wavelengths increase, there's a pronounced trough, a gap in the expected radiation that has physicists scrambling for explanations. One leading theory points to the cold dust lurking between galaxies. Unlike the warmer dust found near stars, these frigid particles, chilled to just a few degrees above absolute zero, emit most of their light at longer infrared wavelengths. When scientists model their contributions, they find a natural drop-off around 2 microns, a spectral fingerprint that could account for the observed dip. But there's a wrinkle. The amount of cold dust required to produce this effect would be staggering, far more than our current surveys of interstellar material suggest exists. If this explanation holds, we've severely underestimated how much of this icy cosmic debris floats in the voids between galaxies. Another possibility takes us back to the universe's earliest stars. Population 3 stars, those primordial giants made of pure hydrogen and helium, would have emitted intense ultraviolet light. Over billions of years, the expansion of space would stretch this radiation into the infrared, potentially creating a distinctive spectral feature around 2 microns as the light redshifts. But just like the cold dust theory, this idea runs into a numbers problem. The dip's depth implies these stars were either far more numerous or burned in ways we haven't yet accounted for, leaving theorists to wonder if we're missing a key piece of stellar evolution's puzzle. Then there's the dark horse candidate, quantum anomalies in the fabric of spacetime itself. Some speculative models suggest that certain particle interactions in the early universe could have left imprints on the infrared background, including a dip at specific wavelengths. These theories, while still on the fringe, propose that phenomena like action-like particles or even extra-dimensional physics might subtly alter how light propagates across cosmic distances, creating spectral quirks like the 2-micron drop. What makes this anomaly so fascinating isn't just the mystery of its origin, it's the way it challenges our assumptions about the universe's building blocks. Whether it's hidden reservoirs of cold dust, echoes of the first stars, or something even more exotic, the CIB dip reminds us that even in the quietest corners of the cosmos, there are still surprises waiting to be uncovered. And with each new observation, we edge closer to understanding whether this dip is a cosmic footnote or a signpost pointing toward undiscovered physics. Imagine a galaxy without dust, no swirling clouds of carbon and silicon, no gritty particles dimming its light, just pristine hydrogen and helium glowing in the void. It sounds like something from a theoretical physicist's sketchbook, yet the cosmic infrared background might be showing us exactly that. One of its most puzzling anomalies suggests that the universe's earliest galaxies could have formed without the very ingredient we thought was essential to their evolution: dust. This isn't just a minor discrepancy, it's a challenge to our fundamental understanding of how galaxies are born. Dust plays a starring role in modern galaxies. It absorbs ultraviolet and visible light from stars, warms up, and re-emits that energy as infrared radiation. That's why dusty galaxies shine so brightly in infrared surveys. But when astronomers trace this logic back to the cosmic dawn, something strange emerges. The infrared background's fluctuations, those patchy variations in brightness, don't always align with the dust-rich galaxies we see today. Some regions appear too smooth, too clean, as if the light traveled unscattered through galaxies devoid of dust altogether. This throws a wrench into our standard models. After all, dust isn't just cosmic decoration, it's a byproduct of star formation itself. When massive stars explode as supernova or shed their outer layers, they spew heavy elements like carbon and oxygen into space, where they clump into dust grains. If early galaxies lacked dust, it implies they either formed stars in an entirely different way or somehow avoided the messy aftermath of stellar death. One radical explanation suggests that the first galaxies were dominated by population, 3 stars, those mythical, metal-free giants made purely of hydrogen and helium. Without heavy elements, these stars wouldn't have produced dust, and their galaxies would glow primarily in ultraviolet light, leaving little infrared trace. But here's the catch: even if these pristine stars dominated, later generations of metal-rich stars should have quickly polluted their galaxies with dust. Unless, of course, something prevented that pollution from accumulating. That's where another theory comes in: galactic winds. In the early universe, fierce outflows of gas powered by supernova or ravenous black holes might have blown dust clear out of fledgling galaxies before it could settle. Imagine a cosmic hurricane scouring a galaxy clean, leaving it transparent to its core. Observations of some distant quasars support this idea, showing evidence of powerful winds capable of ejecting dust on staggering scales. But not everyone's convinced. Skeptics argue that even if winds were rampant, trace amounts of dust should linger, enough to leave some infrared imprint. The fact that we're seeing galaxies with zero dust signature pushes the limits of plausibility. Could there be another factor at play, like an unknown quenching mechanism that suppressed dust formation entirely? Or might we be misinterpreting the data? Some researchers propose that what looks like dust-free galaxies could actually be systems where dust is there but unusually cold, emitting at longer wavelengths than our telescopes can easily detect. The implications ripple far beyond infrared astronomy. If early galaxies were truly dust-free, it reshapes our understanding of how quickly heavy elements spread through the cosmos and how soon life's building blocks became available. It also poses practical challenges for upcoming telescopes like the James Webb Space Telescope, which relies on dust signatures to study the universe's first galaxies. If those galaxies are dustless, they'll appear radically different than we've anticipated. What makes this anomaly so electrifying is the way it forces us to question not just what we see, but what we assume. Every model of galaxy evolution starts with dust as a given, but the cosmic infrared background whispers a tantalizing alternative. What if, in the beginning, the universe built its galaxies in the barest, most elemental way possible? The answer might rewrite not just a footnote in astrophysics, but an entire chapter. Hidden within the cosmic infrared background's subtle flickers lies a shadow of the universe's most transformative moment, the cosmic dawn. This wasn't just the birth of the first stars, it was the ignition of existence itself, when the pitch-black void of space filled with light for the very first time. And now, billions of years later, the faint infrared ripples we detect might be carrying echoes of that primordial sunrise, offering clues about how the universe woke from its dark ages. During the epoch of reionization, a period starting roughly 200 million years after the Big Bang, the first stars and galaxies began punching holes in the cosmic fog. Until then, the universe was a featureless sea of neutral hydrogen gas, soaking up light like a colossal sponge. But as these early stellar behemoths flickered to life, their intense ultraviolet radiation ionized the surrounding gas, stripping electrons from atoms and transforming the cosmos from opaque to transparent. This was the moment light broke free, and the universe as we know it began to take shape. The cosmic infrared background's fluctuations could be our backstage pass to this epoch. Here's why: as those first stars and galaxies ionized their surroundings, their radiation didn't just vanish, it interacted with the matter around it, heating dust and gas, which then re-emitted the energy at longer wavelengths. Over billions of years, that light stretched into the infrared, becoming part of the CIB's patchy glow. By mapping these irregularities, astronomers are essentially reading a cosmic fossil record, tracing where and how violently reionization occurred. But the plot thickens. Some regions of the infrared background show unexpected clustering, bright knots that suggest the first stars didn't ignite uniformly. Instead, they might have flared to life in concentrated bursts, like wildfires spreading through a dry forest. This challenges the assumption that reionization was a slow, steady process. If the CIB's patterns hold up, they could reveal that the universe's enlightenment came in fits and starts, driven by rare, ultra-bright galaxies or even exotic objects we've yet to identify. There's also the tantalizing possibility that these fluctuations encode secrets about dark matter's role in cosmic dawn. Simulations show that dark matter's gravitational pull would have guided where the first stars formed, creating a blueprint for ionization. If the CIB's irregularities align with dark matter's hidden scaffolding, it would be smoking gun evidence of how this mysterious substance shaped the universe's first light. Yet for all its promise, this cosmic dawn signal remains stubbornly enigmatic. The infrared background's noise contamination from local dust, faint galaxies, and instrument limitations makes it like trying to hear a whisper in a hurricane. New telescopes like the James Webb Space Telescope are helping cut through the static, but even their sharp eyes struggle to isolate the faintest ripples from those early epochs. What makes this anomaly so extraordinary isn't just the science, it's the sheer poetry of it. We're not just studying light, we're witnessing the universe's first sunrise, frozen in time and stretched across the sky. Every irregularity in the infrared background is a brushstroke in a self-portrait the cosmos began painting billions of years ago. And as we learn to read its strokes, we might finally understand how darkness gave way to light. Light doesn't always travel in straight lines, sometimes it twists. This subtle property, called polarization, occurs when light waves oscillate in a preferred direction, often after scattering off dust or reflecting from cosmic surfaces. Most of the infrared background's light is unpolarized, its waves jumbled in all directions. But nestled within this glow, astronomers have spotted something strange. Faint, unexpected patches where the infrared light is polarized, aligning in ways that defy conventional explanations. These anomalous signals are more than just curiosities. They could be cosmic breadcrumbs leading us toward undiscovered physics or revealing flaws in our most sensitive instruments. The first clues emerged when researchers mapped the infrared sky's polarization patterns, expecting to see smooth, predictable variations tied to known sources like interstellar dust. Instead, they found sharp, isolated regions where the polarization angles didn't match their surroundings, like compass needles suddenly pointing the wrong way. Some of these regions showed polarization degrees far higher than dust alone could produce, while others exhibited spiraling patterns with no clear origin. It was as if something invisible had reached out and combed the light into unnatural alignments. One leading theory points to magnetic fields woven through the fabric of space. Cosmic magnetism is notoriously difficult to study, but we know it permeates galaxies and even the voids between them. If particularly strong or twisted magnetic fields existed in the early universe, they might have polarized infrared light from the first stars or galaxies, leaving behind these ghostly imprints. The challenge: no known magnetic phenomenon explains the scale or intensity of these signals. To match the observations, we'd need fields orders of magnitude stronger than anything observed nearby, or an entirely new mechanism for amplifying polarization across vast distances. Then there's the exotic physics angle. Certain theories beyond the standard model predict that hypothetical particles like actions or primordial magnetic monopoles could interact with light in ways that induce polarization. If these particles clustered in specific regions during the universe's infancy, they might have imprinted their presence on the infrared background like cosmic graffiti. Even more radically, some speculate that spacetime itself might have quantum-level imperfections, tiny twists or fractures left over from the Big Bang, that subtly alter light's journey, creating polarization anomalies. But before we rewrite physics textbooks, there's the mundane possibility: instrumental glitches. Polarization measurements are fiendishly delicate, vulnerable to everything from telescope jitters to microscopic imperfections in detectors. Could these signals simply be echoes of human error? Teams have cross-checked data from multiple observatories, and while some anomalies persist, others vanish under closer scrutiny. The line between discovery and artifact remains frustratingly blurry. What makes these polarization quirks so compelling is their duality. They could be the whisper of something profound or the static of our own limitations. Either way, they force us to look deeper, to question not just what we see but how we see it. And in that tension between cosmic mystery and human ingenuity, discoveries are born. Some patches of the cosmic infrared background don't just defy expectations, they defy cosmic drama altogether. While most of the CIB ripples with fluctuations, telling the chaotic story of early galaxies and violent star formation, certain regions are eerily calm. Too calm, these zones lack the expected clumpiness, appearing almost polished smooth against the otherwise textured infrared sky. At first glance, it might seem like a minor quirk, but this too smooth problem strikes at the heart of how we think the universe built its grandest structures. The puzzle begins with cold dark matter, the invisible scaffolding thought to guide galaxy formation. According to our best models, slight density variations in the early universe, tiny quantum ripples amplified by inflation, should have seeded all later structure. Gravity pulled matter into these denser regions, creating a cosmic web of filaments and voids where galaxies eventually blossomed. That's why we expect the infrared background to mirror this web, with brighter knots tracing galaxy clusters and fainter streaks marking the emptier gaps. But the anomalously smooth regions refuse to comply. They don't just have fewer fluctuations, they lack them almost entirely, as if someone took a cosmic iron to that patch of space. One possibility is that these zones are genuine fossilized voids, regions where dark matter's pull was mysteriously weaker, leaving them starved of stars and galaxies. Yet simulations struggle to produce voids this extreme without tweaking fundamental physics. Even the emptiest corners of the modern universe, like the infamous Boötes void, still show faint infrared wisps from wandering stars or distant background galaxies. These CIB deserts, by contrast, are pristine. Another explanation points to timing. If reionization, the epoch when the first stars ionized the universe's hydrogen fog, happened unevenly, some regions might have been quenched early, shutting down star formation before it could leave an infrared imprint. Imagine a forest where some patches were doused in water before the wildfire spread. Those areas would remain unnaturally green. Similarly, if something, perhaps a surge of radiation from an early supermassive black hole or a localized dark matter anomaly, halted star formation in these zones, they'd appear smooth in infrared surveys today. Then there's the radical notion that these smooth patches aren't empty at all. They could be hiding ultra-diffuse galaxies, sprawling collections of stars so thinly spread they're virtually invisible. Alternatively, they might be dominated by dark matter halos that somehow failed to ignite stars, leaving behind shadowy structures that don't glow in infrared. Both ideas flirt with the limits of our detection. If something is dark enough or diffuse enough, even our best telescopes might miss it. But the most tantalizing hypothesis is also the most unsettling. What if the too smooth problem reveals a flaw in our understanding of dark matter itself? Most models assume cold dark matter moves sluggishly, clumping easily to form galaxies. Yet if dark matter has even a tiny amount of intrinsic motion, if it's warm rather than cold, it could smooth out small-scale fluctuations, preventing structure from forming in certain regions. This would leave pockets of unnaturally placid infrared light exactly as we're observing. The implications are staggering. Dark matter's temperature isn't just a technical detail, it determines how the universe organizes itself. Warm dark matter would mean galaxies formed later and in fewer numbers, rewriting the cosmic timeline. It might even explain other lingering puzzles, like the scarcity of dwarf galaxies around the Milky Way. For now, the smooth CIB regions remain cryptic, their silence echoing louder than any signal. Whether they're cosmic oddities, measurement errors, or keys to dark matter's true nature, they remind us that sometimes the universe's quietest corners shout the most profound questions. Deep in the far infrared realm of the cosmic spectrum, a peculiar anomaly flickers at 70 microns, a wavelength so long it borders on microwave territory. Unlike the familiar glow of star-forming regions or the gentle hum of interstellar dust, this signal is stubbornly brighter than it should be, a cosmic shout where we expected a whisper. Known as the 70-micron excess, this anomaly paints a portrait of something unseen, either an overlooked population of frigid celestial objects or a whisper from the invisible realm of dark matter itself. The first clue lies in temperature. To emit strongly at 70 microns, an object must be unthinkably cold, hovering just a few degrees above absolute zero. Ordinary interstellar dust, while chilly by human standards, is usually too warm to dominate this far into the infrared. That's why astronomers initially suspected a hidden reservoir of ultra-cold dust. Particles drifting in the deepest voids between galaxies, so frigid they've slipped past our surveys unnoticed. If such dust exists in vast quantities, it could explain the excess, glowing dimly like a cosmic freezer humming in the dark, but the numbers pose a problem. To match the observed signal, this dust would need to fill intergalactic space in amounts that challenge our understanding of how matter is distributed. Galaxies should have ejected some dust into their surroundings, but not enough to account for the 70-micron excess's sheer scale. Unless, of course, there's a mechanism we've missed, something propelling dust far beyond galactic borders, like cosmic winds or explosive galactic mergers on a scale we've yet to witness. That's where the dark matter hypothesis takes the stage. Certain theoretical particles, like sterile neutrinos or actions, could decay into photons with wavelengths clustering around 70 microns after accounting for cosmic expansion. If true, this excess wouldn't be dust at all, but the collective glow of invisible particles fading into light across the universe. The idea gains traction because it solves two puzzles at once: the infrared anomaly and the search for dark matter's true nature. Yet skeptics point out that such decays should produce other detectable signatures, gamma rays or X-rays, that we haven't observed in the expected amounts. Then there's the middle ground, a cosmic interplay of both. Some theorists propose that dark matter's gravitational influence could have sculpted the distribution of cold dust, funneling it into the same vast, unseen structures that galaxies cling to. In this scenario, the 70-micron excess would be a joint signature, a collaboration between the ordinary and the invisible. It's a compelling compromise, but one that demands more evidence to confirm. What makes this anomaly so captivating isn't just the mystery of its origin, it's the way it stretches our tools to their limits. 70 microns sits in an observational blind spot, too long for most infrared telescopes to study crisply, yet too short for radio instruments to capture cleanly. Upcoming observatories like the upcoming Speaker mission aim to bridge this gap, offering sharper views of this elusive wavelength. Until then, the 70-micron excess remains a cosmic Rorschach test, reflecting back our theories, our hopes, and the tantalizing possibility that even the coldest, quietest corners of the universe still have stories to tell. If the cosmic infrared background is the universe's quiet hum, then the X-ray background is its roar, a high-energy crackle of black holes, exploding stars, and superheated gas. At first glance, these two cosmic echoes should tell the same story, just in different wavelengths. but when astronomers line them up, something doesn't add up. The infrared and X-ray backgrounds don't sync the way they should. Whole swaths of the sky glow brightly in one while staying suspiciously dim in the other, as if the universe forgot to flip a switch. This mismatch isn't just a technical hiccup, it's a cosmic whodunit, hinting at hidden populations of energetic objects or even entirely new astrophysical processes. Take active galactic nuclei, or a GN for short. These powerhouses, fueled by supermassive black holes devouring matter, should light up both backgrounds. As material spirals into the black hole's maw, friction heats it to millions of degrees, unleashing torrents of X-rays. Meanwhile, dust near the AGN absorbs some of that energy and re-emits it as infrared. In theory, we'd expect X-ray and infrared signals from these monsters to correlate neatly. Yet when we map them, the overlap is patchy at best. Some regions teeming with infrared show scant X-rays, while X-ray hotspots sometimes lack the expected infrared counterparts. It's like hearing thunder without seeing lightning. The energy's there, but the trail goes cold. One explanation points to shrouded black holes. Not all AGN are created equal. Some are obscured, buried under such thick layers of gas and dust that their X-rays get absorbed before reaching us. Their infrared light, however, slips through, creating a disconnect in the data. If enough of these hidden giants lurk in the cosmic background, they could explain the imbalance. But recent surveys suggest there aren't enough obscured AGN to account for the discrepancy unless, of course, we've underestimated just how sneaky these black holes can be. Then there's the wild card, star formation. Young, massive stars don't emit X-rays, but their furious winds and supernova can accelerate particles to extreme energies, generating diffuse X-ray halos around galaxies. Meanwhile, the dust in these stellar nurseries glows brightly in infrared. The catch, the X-rays from star-forming regions are typically fainter and more spread out than those from a GN, making it hard to attribute the background mismatch solely to them. Unless, that is, the early universe hosted a hyperactive breed of star formation we've yet to observe directly, one that produced X-rays in unexpected ways. The plot twists further when we consider truly exotic possibilities. Could some of the missing X-rays be the echoes of decaying dark matter particles? Certain theories predict that dark matter annihilation could produce both X-rays and infrared photons, potentially bridging the gap. Others speculate about primordial black holes, those hypothetical relics from the Big Bang evaporating via Hawking radiation and leaving behind X-ray signatures without the usual infrared baggage. These ideas dance on the edge of known physics, but the persistence of this anomaly keeps them in play. What makes this mismatch so compelling is how it forces us to question the universe's ledger. Energy can't just vanish, it has to go somewhere. If the books don't balance, we're either missing a cosmic accountant or we've misread the entries. Every discrepancy is a clue, pointing toward hidden chapters in the story of how the universe organizes its light and energy. And until we solve it, the infrared and X-ray backgrounds will keep whispering their discordant secrets, challenging us to listen more closely. One of the most poetic ideas in astronomy is that light never truly dies, it just stretches, fades, and echoes across the cosmos. And hidden within the cosmic infrared background, there might be whispers of some of the most violent events the universe has ever witnessed. This is the CIB echo hypothesis, the tantalizing notion that certain infrared anomalies are the ghostly afterglow of supermassive black hole collisions that shook the fabric of spacetime billions of years ago. Picture two black holes, each weighing billions of times the mass of our Sun, locked in a gravitational death spiral. As they inch closer over millennia, their dance warps spacetime itself, sending out ripples we now call gravitational waves. But their final merger isn't just a silent implosion, it's a cosmic fireworks show. The surrounding gas and dust, heated to unimaginable temperatures by the violence of the collision, would have erupted in an infrared blaze so bright it could outshine entire galaxies. Fast forward to today, that cataclysmic flash has long since faded from visible view, stretched by the expansion of the universe into the infrared, a whisper of heat lingering at the edge of detection. Theoretically, if enough of these mergers happened during the cosmos's formative years, their combined afterglow could imprint as subtle excesses or anomalies in the CIB, like fossilized shockwaves frozen in the sky. What makes this idea so compelling is how neatly it solves multiple puzzles at once. Certain unexplained infrared patches align eerily well with predictions of where and when ancient black hole mergers should have occurred, based on our understanding of galaxy evolution. These regions are often too bright to be explained by standard star formation, yet too diffuse to trace back to any single known source. They're cosmic mirages, glowing faintly with no obvious engine unless you consider black holes that vanished billions of years ago. But proving this isn't just a beautiful story requires looking for invisible fingerprints. Merging black holes should leave behind more than just infrared echoes. They'd also sculpt their surroundings in telltale ways. For instance, the recoil from a lopsided collision can kick the merged black hole clean out of its host galaxy, stripping away gas and leaving behind a dark galaxy with no central engine. If the CIB anomalies coincide with such ghostly systems, it would be a smoking gun. There's also the matter of timing. The echoes we're seeing, if real, would have to come from mergers during cosmic noon, the peak of galaxy formation around 10 billion years ago. That's when supermassive black holes were feasting most voraciously, and mergers would have been rampant. But here's the catch. The infrared background's resolution is too fuzzy to pin down exact dates, leaving room for debate. Are we seeing a chorus of echoes from many mergers or just a few deafening ones? Skeptics point to alternative explanations. Could these infrared patches be the lingering heat of quasar remnants, black holes that flickered out after exhausting their fuel? Or might they be something entirely unrelated, like the collective glow of ancient supernova we've misread? The debate thrives because at these distances and timescales, every signal is fragmentary, like trying to reconstruct a symphony from a handful of scattered notes. Yet, even if the CIB echo hypothesis remains unproven, it reshapes how we think about the universe's memory. Light isn't just information, it's history, carrying tales of events we could never witness directly. Every anomalous flicker in the infrared sky might be a chapter from a story written in gravity and fire, waiting for us to learn how to read it. We think of the universe's early years as a time of simplicity, just hydrogen, helium, and the faintest whisper of lithium, the only elements forged in the Big Bang's fiery aftermath. Everything else, the carbon in our bones, the oxygen we breathe, the iron in our blood, had to be cooked up later, in the hearts of stars or the explosions of supernova. But when astronomers trace this cosmic alchemy through the infrared background's glow, they hit a snag. The metals are missing, or rather, they're not where they're supposed to be. The CIB's spectral fingerprints suggest pockets of the early universe were either drowning in heavy elements or suspiciously empty of them, with no tidy gradient in between. It's as if the cosmos skipped a step in its own chemical evolution, leaving us to piece together how stardust first spread through the void. Consider the smoking gun, certain infrared wavelengths that should glow brightly, lit by the thermal echoes of early metals, instead fall eerily silent. These gaps imply some regions of the infant universe remained stubbornly pristine long after stars began churning out heavier elements. That shouldn't happen. Supernova are nature's ultimate mixers, their shockwaves powerful enough to fling newly forged metals far into intergalactic space. Even the faintest dwarf galaxies from that epoch should have polluted their surroundings with at least trace amounts of carbon or oxygen. Yet the CIB's uneven metal signatures suggest vast territories untouched by this chemical enrichment, like finding deserts in the middle of an ocean. One explanation throws star formation into chaos. Perhaps the first supernova weren't just explosions but cosmic cannons, firing jets of metal-rich gas so violently that they punched clean out of their host galaxies, leaving behind barren cores while seeding distant, unexpected regions. Simulations show these runaway metals could travel millions of light-years before settling, creating bizarre patchworks of enrichment and deprivation. If true, it would mean the universe's first heavy elements didn't disperse evenly but ricocheted through space like shrapnel, leaving some areas barren and others bizarrely overstocked. Then there's the dark matter wrinkle. Maybe the distribution of metals wasn't just about stellar explosions but about invisible scaffolding. Dark matter's gravitational pull could have funneled metals into specific zones, like cosmic watersheds directing the flow of chemical rivers. Certain CIB anomalies align suspiciously well with the predicted locations of primordial dark matter filaments, those vast thread-like structures linking galaxies. If metals pooled along these hidden highways, it would explain why some infrared wavelengths cluster in odd thread-like patterns, as if tracing the bones of a skeleton we can't quite see. But the most radical idea flips the script entirely. What if the missing metals aren't missing at all, but hiding in plain sight? Dust grains in the early universe might have formed differently than they do today, clumping into ultra-cold aggregates that emit infrared light at wavelengths we've overlooked. Or worse, what if our assumptions about early stellar chemistry are flawed? The first stars might have forged elements in proportions we don't expect, producing bizarre isotopes that cool or emit light in ways our models don't account for. It's a humbling thought. The periodic table itself might not be the universal constant we imagined, but a rulebook with early edition quirks we're only now glimpsing. This anomaly isn't just about accounting for lost elements. It's about decoding the universe's first recipes for complexity. Metals aren't just cosmic byproducts, they're the raw materials for planets, life, and everything we know. If their distribution was as haphazard as the CIB suggests, it could mean the difference between a galaxy ripe for rocky worlds and one forever stranded in chemical poverty. The infrared sky holds the receipts for this grand cosmic transaction, if only we learn to read them right. Among the cosmic infrared background's many riddles, few are as stubborn as the spectral oddities that appear where no astrophysicist expects them. Picture a musician playing a familiar song only to hit notes that don't belong, notes no instrument should produce. That's what astronomers face when analyzing the CIB's spectrum. Unexpected dips and bumps, spectral kinks that refuse to align with the smooth curve of known cosmic light sources. These aren't mere statistical flukes. They're deviations so pronounced they've sparked debates about everything from hidden quantum processes to flaws in our most fundamental assumptions about light itself. Take the abrupt dip near 15 microns, a wavelength where interstellar dust typically shines brightest. Instead of the anticipated peak, there's a trough, as if something in the universe is selectively absorbing that specific light. Dust models can't explain it, neither can known molecules or ions. One radical theory suggests we're seeing the shadow of exotic ices, frozen compounds like methane or ammonia clinging to dust grains in the void between stars. These ices would absorb 15-micron light before re-emitting it at longer wavelengths, creating the observed dip. But here's the catch: to match the signal's depth, these ices would need to coat dust grains in impossible quantities, far beyond what chemistry predicts for the early universe. Then there's the baffling bump at 9 microns, a frequency usually dominated by the spectral fingerprints of silicon-rich dust. The excess here is too sharp, too narrow to be explained by ordinary grain heating. Some researchers speculate it could be the calling card of nanoparticles, tiny specks of carbon or silicate small enough to behave unlike bulkier dust, emitting light in quantum-sized bursts. Others wonder if we're glimpsing the afterglow of photodissociation regions, violent zones where starlight tears molecules apart, leaving behind fragmented atoms that glow at odd wavelengths. But the real enigma is the so-called 3-micron plateau. a broad, elevated stretch of infrared light that defies all conventional templates. No known star, galaxy, or dust population emits quite this way. One provocative idea ties it to hydrogenated amorphous carbon, a quirky form of cosmic soot whose irregular atomic structure gives it unusual spectral flexibility. If vast clouds of this material drifted through the early universe, they might account for the plateau's shape. Yet even this leaves gaps, failing to explain why the signal appears stronger in some directions than others. The most daring explanations leap beyond astrophysics entirely. Certain quantum gravity models predict that space-time itself might have a granular structure at microscopic scales. If true, photons traveling across billions of light-years could subtly interact with this fabric, their wavelengths nudged in ways that imprint odd features on the cosmic background. It's a fringe idea, but the persistence of these spectral anomalies keeps even the wildest hypotheses in play. What makes these quirks so compelling isn't just their mystery, it's what they reveal about how we study the cosmos. Every unaccountable dip or bump is a reminder that light isn't just information. It's a messenger carrying tales of processes we've yet to imagine. And until we decode its full vocabulary, the universe's spectral whispers will keep challenging us to listen more closely. Among the faintest flickers in the cosmic infrared background lies one of the most perplexing possibilities: an entire population of galaxies that defy everything we know about how galaxies should look. These aren't just dim or distant, they might be fundamentally different, built not around blazing stars but around something far more mysterious: dark matter. Astronomers call them dark galaxies, cosmic ghosts that could explain some of the CIB's strangest anomalies while reshaping our understanding of how structures form in the universe. The idea begins with a simple mismatch. When we tally up all the light from known galaxies and compare it to the cosmic infrared background, there's a glaring gap. Some regions glow brighter than the combined output of every star and nebula we've catalogued, as if hidden celestial engines are humming just beyond our sight. One compelling explanation: galaxies where stars are vanishingly rare, their mass and gravity dominated instead by dark matter. Without the usual stellar fireworks, these shadows of the cosmic web would emit almost no visible light. But their sparse, scattered stars, along with any dust or gas stirred by dark matter's gravitational tides, could still radiate faint whispers of infrared. Finding proof is like searching for black cats in a pitch-black room. Dark galaxies, by definition, lack the starlight that makes ordinary galaxies visible. But hints have emerged in unexpected places. Take the infamous dark galaxy candidate, HI 1225+01, detected not by its stars but by the subtle ripples it creates in surrounding hydrogen gas. Its gravitational pull suggests the mass of a small galaxy, yet it emits less than 1% the light expected for its size. Similar objects like Dragonfly 44 in the Coma cluster flaunt stunningly low star-to-dark matter ratios, raising the tantalizing question: could these oddballs be the tip of an invisible iceberg, with countless more lurking in the CIB's unresolved glow? The implications ripple far beyond infrared astronomy. If dark galaxies are real and abundant, they could solve multiple cosmic puzzles at once. For starters, they'd help balance the universe's missing satellite problem: the curious shortage of small galaxies orbiting large ones like the Milky Way. Simulations predict thousands of such satellites, yet we've found only dozens. Dark galaxies could account for the discrepancy hiding in plain sight. They might also explain certain gravitational lensing anomalies, where unseen masses bend light more than visible matter can account for. But the true allure lies in what these shadowy structures could reveal about dark matter itself. Unlike ordinary galaxies, where stars and gas muddle the gravitational picture, dark galaxies would be pristine laboratories. Their rotation curves, gas dynamics, and interactions would reflect dark matter's behavior almost exclusively, offering clues about whether it's cold, warm, or something even stranger. Some models even suggest dark galaxies could harbor exotic stellar populations, failed stars like brown dwarfs or rogue planets, creating a faint infrared haze without the usual stellar brilliance. Of course, skepticism lingers. Alternative explanations abound. Perhaps these are just ordinary galaxies cloaked in unprecedented dust, or the shredded remnants of past collisions. Others argue that without direct dark matter detection, the case remains circumstantial. Yet as telescopes like the James Webb Space Telescope peer deeper into the infrared sky, the hunt intensifies. Every unexplained CIB fluctuation could be a breadcrumb leading to these cosmic phantoms, if we're willing to chase shadows. What makes the dark galaxy enigma so thrilling is its audacity. It challenges not just what we see, but how we define a galaxy in the first place. Must they be islands of stars, or can they be something darker, quieter, and infinitely stranger? The infrared background's anomalies suggest the universe's story is far richer and far more mysterious than we ever imagined. One of the greatest turning points in cosmic history wasn't the birth of stars or galaxies, it was the moment the universe itself became transparent. For hundreds of millions of years after the Big Bang, space was a soupy fog of neutral hydrogen gas, so thick with particles that light couldn't travel far before being absorbed. Then something changed. A mysterious process called reionization began clearing this haze, stripping electrons from hydrogen atoms and transforming the cosmos into the crystal-clear expanse we know today. But when scientists compare predictions of how this happened to the actual fingerprints left in the cosmic infrared background, the stories don't match. The CIB reveals a reionization process far patchier, more chaotic, and possibly earlier than our best models predict, a disconnect that threatens to rewrite our understanding of the universe's adolescence. The standard tale goes like this. The first stars and galaxies flickered on around 200 million years after the Big Bang, their intense ultraviolet radiation slowly ionizing the surrounding hydrogen in expanding bubbles. Over several hundred million more years, these bubbles overlapped until the entire universe became transparent like watching fog lift unevenly across a lake before finally clearing all at once. Simulations based on this scenario predict a specific pattern in the infrared background's fluctuations. Smoother variations where reionization happened gradually, sharper edges where bubbles collided. But the CIB shows something else entirely: jagged, irregular patches suggesting some regions ionized shockingly fast while others lagged behind, as if cosmic transparency wasn't a steady march but a series of fits and starts. This inconsistency points to a glaring gap in our knowledge. What exactly powered reionization? The usual suspects, early galaxies, don't seem up to the task. Based on the number and brightness of galaxies we've spotted from that epoch, there simply weren't enough to ionize the entire universe so quickly. Even if every known galaxy worked overtime, the math falls short by a factor of 2 or more. That's led researchers to propose wildcards. Maybe supermassive black holes formed earlier than thought, their voracious feeding producing torrents of ionizing radiation. Or perhaps the first stars were unimaginably efficient at stripping electrons, burning hotter and brighter than modern stellar models allow. But the most intriguing clue lies in the CIB's lopsided ionization patterns. Some regions appear to have reionized hundreds of millions of years earlier than others, a spread too wide to explain by standard galaxy formation alone. This has sparked controversial theories about pre-ionization, events cataclysms like the explosive deaths of the universe's very first stars, or even more exotic phenomena like decaying dark matter particles flooding space with ionizing energy long before galaxies took shape. If true, reionization didn't have a single trigger but multiple overlapping causes, each leaving distinct infrared fingerprints we're only now learning to read. The stakes in this puzzle couldn't be higher. Reionization didn't just clear the cosmic fog, it set the stage for everything that followed. The timing and mechanics of this process determined how quickly galaxies could grow, how light permeated the universe, and ultimately, how conditions became ripe for planets and life. If our models are wrong, we may be misunderstanding foundational chapters in cosmic history. The CIB's conflicting signals are more than just data points. They're echoes from an era when the universe fundamentally transformed itself, and we're only beginning to grasp how. Dust isn't supposed to burn this hot, not in the early universe at least. That's the puzzle at the heart of Anomaly 29, where patches of the cosmic infrared background glow with the unmistakable signature of dust heated to temperatures we'd expect near blazing stars or active black holes. But here's the catch. These signals date back to a time when the universe was barely a toddler, a mere billion years old or less. Conventional wisdom says dust that early should be frigid, drifting in the quiet outskirts of fledgling galaxies, not scorching hot enough to leave searing fingerprints in the infrared sky. The conundrum starts with basic physics. Dust grains, tiny flecks of carbon, silicon, and other minerals, absorb starlight and re-emit it as infrared radiation. The hotter the environment, the shorter the wavelengths they glow at. In the modern universe, we see this around star-forming regions or the accretion disks of black holes where energy is abundant. But in the cosmic dawn, galaxies were smaller, stars fewer, and black holes rarer. There simply shouldn't have been enough localized energy to heat dust to the temperatures the CIB reveals. It's like finding a forest fire in the middle of an ice age. The fuel and ignition source don't add up. One radical explanation points to supermassive black holes growing at breakneck speeds. If these monsters formed not through gradual mergers but via direct collapse, a process where vast gas clouds bypassed star formation entirely and imploded straight into black holes, they could have generated staggering amounts of heat in their infancy. Picture a newborn black hole, not yet weighed down by the slow digestion of stars, instead feasting on the dense primordial gas around it. The resulting radiation would have been intense enough to flash fry nearby dust, imprinting the infrared background with these anomalous hotspots. Yet even this dramatic scenario struggles to account for the sheer number and distribution of these overheated regions. Then there's the stellar rebellion hypothesis. What if the first stars didn't play by the rules? Modern stars form in relatively sedate clouds, but population 3 stars. Those hypothetical metal-free giants might have been born in hyper-dense clusters, packing thousands of stellar behemoths into volumes smaller than the solar system. Their combined ultraviolet fury could have heated surrounding dust to extreme temperatures before the stars themselves vanished in supernova or collapsed into black holes. Simulations show such clusters might have existed briefly like cosmic flashbulbs, leaving behind infrared echoes of their fiery lives. But the real curveball comes from an unexpected quarter: dark matter. Certain theoretical particles, like weakly interacting massive particles or WIMP, could annihilate upon collision, releasing bursts of energy. If these interactions were concentrated in the early universe's densest regions, they might have heated dust indirectly, creating infrared hotspots without the need for stars or black holes at all. It's a long shot, but the idea gains traction because it could simultaneously explain other CIB anomalies, like unexplained fluctuations in the background's large-scale structure. The implications ripple far beyond dusty astrophysics. If the too hot dust is real, it suggests the early universe was far more violent and energetic than we've imagined, with processes we've either overlooked or misunderstood. It challenges our timelines for galaxy formation, our models of stellar birth, even our understanding of how matter behaves under extreme conditions. Every overheated speck in the infrared sky is a challenge, a dare to look deeper and rethink the universe's wild youth. And until we solve it, this anomaly will keep burning, a cosmic mystery too hot to ignore. Some cosmic signals don't just fail to match, they actively push each other away. Among the rarest and most baffling anomalies in the infrared background are regions where it seems to recoil from the cosmic microwave background, the CMB, as if repelled by some unseen force. This bizarre anti-correlation shows up in select patches of sky where the CMB's glow dims precisely as the CMB brightens, creating valleys in one background that mirror peaks in the other. It's a cosmic seesaw that defies every expectation because these two signals shouldn't even be aware of each other, let alone locked in a gravitational tug of war. To grasp why this is so strange, consider their origins. The CMB is the afterglow of the Big Bang, a snapshot of the universe just 380,000 years old, frozen in microwaves. The SIB, by contrast, is a scrapbook of everything that came after, the accumulated light of stars and galaxies spanning billions of years. They're like two strangers separated by eons, one from the dawn of time, the other from its unfolding story. Yet in these peculiar zones, they move in opposition, as if bound by some hidden thread. One possible explanation digs into the physics of how light interacts with matter. When cosmic microwave photons travel through galaxy clusters, they can gain energy via the Sunyaev-Zeldovich effect, a subtle boost as they scatter off hot electrons in the cluster's gas. This would make those regions appear brighter in the CMB. Meanwhile, the same clusters might block or redirect infrared light from more distant sources, casting shadows in the CIB. The result, an artificial anti-correlation, a cosmic mirage where two unrelated processes create the illusion of a deeper connection. But skeptics point out a flaw: the anti-correlation persists even where galaxy clusters are sparse. That's led to more exotic theories, like the idea of primordial magnetic fields woven through space during inflation. These hypothetical fields, if strong enough, could have sculpted both backgrounds simultaneously, twisting the CMB's polarization while funneling dust into configurations that leave odd infrared voids. It's a stretch, but the magnetic field's dual influence might explain why the anti-correlation appears in such specific, thread-like patterns. Then there's the dark matter angle. Certain models suggest dark matter particles could decay into both microwave and infrared photons, but with a catch: the processes might be mutually exclusive, like a seesaw where producing one type of light suppresses the other. If these decays happened unevenly across the cosmos, they could create pockets where one background rises as the other falls. What makes this anomaly so unsettling isn't just its defiance of known physics, it's the way it blurs the line between the universe's oldest and youngest light. If the connection is real, it implies hidden mechanisms binding epochs that should be independent, as if time itself folds back to link the infant cosmos with its maturity. Until we untangle this knot, these anti-correlated patches will linger as cosmic Rorschach tests, challenging us to decide whether we're seeing a trick of the light or a glimpse of a deeper symmetry. Among the faintest whispers in the cosmic infrared background lies a population so elusive they border on the spectral galaxies, barely clinging to the edge of detection, visible only when their light is pooled together like scattered coins gathered into a single handful. These ghost galaxies defy conventional observation, hiding in plain sight until astronomers employ a clever trick called stacking, layering hundreds or thousands of infrared images atop one another to amplify their collective glow. What emerges is astonishing: entire swarms of dim, distant galaxies that individually slip beneath the noise floor of even our most powerful telescopes, yet together form a significant portion of the CIB's unresolved light. The existence of these phantom galaxies throws a wrench into our understanding of cosmic structure. If they're as abundant as stacking suggests, they could outnumber all known galaxies combined, lurking in the shadows like a cosmic iceberg, with only the brightest tip visible to us. Their extreme faintness implies they're either incredibly small, devoid of the blazing star-forming regions that light up typical galaxies, or so choked with dust that their starlight is smothered before it can escape. Some might be failed galaxies, stunted early in development by lack of gas or dark matter, while others could be relics of a primordial era when most galaxies were born miniature. But the real puzzle lies in their distribution. Unlike their brighter cousins, which cluster along filaments of the cosmic web, ghost galaxies appear scattered almost randomly, some drifting in voids, others haunting the edges of galaxy clusters. This chaotic arrangement hints they might be victims of cosmic bullying, dwarf galaxies stripped of stars and gas by larger neighbors, leaving behind nearly invisible husks. Alternatively, they could represent a distinct class of objects that formed in isolation, born from gas too tenuous to ignite the fireworks of conventional star formation. The implications ripple far beyond cataloging dim lights. If these ghosts are real, they could solve the long-standing missing satellites problem. The discrepancy between the number of small galaxies predicted to orbit large ones like the Milky Way and the paltry few we've actually found. They might also account for a portion of the universe's missing baryons, the ordinary matter that's mysteriously unaccounted for in cosmic inventories. Even their dust, if present in vast quantities, could explain certain infrared excesses that baffle researchers. Yet skepticism lingers. Stacking is a statistical tool, not direct observation, a bit like concluding the existence of fireflies by analyzing the glow of a distant forest without ever seeing individual flashes. Critics argue some signals could be artifacts, subtle instrumental quirks amplified by the process. Others suggest these galaxies might not be separate entities at all, but diffuse halos of stars torn free during galactic collisions, lingering like smoke after a fireworks display. The James Webb Space Telescope is finally bringing these shadows into focus. Early observations have tentatively spotted a few ghostly candidates at the edge of detectability, their spectra bearing the telltale redshift of extreme distance. But confirming their nature requires more than a glimpse. It demands rewriting the rules of galaxy formation to explain why the cosmos would craft hordes of objects so determined to evade our gaze. Until then, these infrared phantoms remain both a tantalizing solution and a haunting reminder of how much we've yet to see. The universe isn't random, it's organized. On the largest scales, matter weaves a vast, intricate tapestry called the cosmic web, where galaxies cluster along gossamer threads of dark matter like dewdrops on a spider's silk. These filaments stretch across billions of light years, connecting galaxy clusters in a delicate lattice of gravity and gas. But here's the twist. While we've long mapped the cosmic web through galaxy surveys and simulations, the cosmic infrared background might be showing us something startling: an infrared shadow of this hidden scaffolding, imprinted in anomalies that trace where no stars or galaxies shine. At first glance, it sounds impossible. The cosmic web's filaments are notoriously sparse, their densities so low they'd make Earth's hardest vacuum seem crowded. Yet certain patches of the CIB glow with unexpected brightness precisely where these filaments should lie, as if the universe left infrared breadcrumbs along its darkest highways. The explanation could lie in the faintest of cosmic processes, intergalactic gas, heated to millions of degrees as it funnels into filaments, emitting soft X-rays that over billions of years redshift into the infrared. Alternatively, dark matter itself might be playing tricks. If hypothetical particles like sterile neutrinos decay within these filaments, they could release infrared photons directly, painting the web's skeleton with ghostly light. The most tantalizing evidence comes from cross-referencing CIB anomalies with gravitational lensing maps, which reveal the cosmic web structure through distortions in background starlight. In multiple regions, unexplained infrared excesses align eerily with filamentary dark matter concentrations, like ink seeping along the edges of an invisible drawing. Some signals even hint at finer substructure knots and intersections where filaments meet, glowing more brightly than the threads themselves. It's as if the CIB is giving us an infrared X-ray of the universe's largest-scale anatomy. Yet skeptics argue these alignments could be cosmic coincidence, without direct spectral signatures tying the anomalies to filamentary gas or dark matter. Alternative explanations persist. One suggests we're seeing the combined glow of countless dwarf galaxies too dim to spot individually, huddling along filaments like fireflies on a wire. Another posits that dust expelled by galactic winds might collect in these gravitational valleys, warming enough to emit infrared without obvious stellar heat sources. The stakes are higher than just mapping hidden structures. If the CIB truly traces the cosmic web, it could reveal how efficiently dark matter funnels gas into galaxies, and why some filaments ignite with stellar fire while others remain barren. It might even expose dark matter's quirks, whether it clumps differently on filamentary scales or interacts in ways we've yet to imagine. Every unexplained infrared flicker along these threads whispers the same question: are we seeing the universe's bones or just the dust clinging to its skin? The cosmic infrared background isn't just a smooth canvas. It's speckled with mysterious knots, dense concentrations of infrared light that clump together like tangled threads in the universe's tapestry. These peculiar structures, known as CIB knots, glow brighter than their surroundings by orders of magnitude, yet when astronomers train their most powerful telescopes on them, they often find nothing. No visible galaxies, no blazing quasars, just an eerie excess of infrared radiation with no obvious source, as if the light is spilling from hidden doorways in space itself. One leading theory suggests these knots could be protoclusters, infant versions of today's massive galaxy clusters, caught in the act of formation during the universe's chaotic adolescence. Imagine a bustling construction site in the cosmos where dozens of young galaxies huddle together, their collective starlight absorbed by thick clouds of dust and re-emitted as infrared. Over billions of years, gravity would pull these galaxies even closer, forging the densely packed clusters we see in the modern universe. The knot's infrared glow, then, might be the thermal echo of that ancient construction frenzy, a snapshot of cosmic urban sprawl in its earliest stages. Yet there's a problem. Some CIB knots are too bright, their infrared output far exceeding what even a nascent protocluster should produce. That's led to wilder ideas, like the possibility of supermassive black holes feasting in unison, their accretion disks pumping out torrents of energy that heat surrounding dust to extreme temperatures. Simulations show that if multiple black holes in a protocluster became active simultaneously, perhaps triggered by a cascading collapse of gas, their combined fury could easily explain the anomalous brightness. But confirming this requires spotting the black holes themselves, which so far remain stubbornly hidden behind veils of dust and time. Then there's the dark matter twist. If these knots trace the densest nodes of the cosmic web, where dark matter filaments intersect, they might harbor exotic physics at play. Certain theories suggest dark matter could decay or annihilate more vigorously in these crowded regions, releasing energy that heats gas or dust indirectly. Others propose that primordial magnetic fields woven into the fabric of space during the Big Bang might have amplified in these knots, creating infrared hotspots through processes we've yet to understand. What makes these knots so mesmerizing isn't just their defiance of explanation. It's their potential to rewrite the story of cosmic structure. Every unexplained concentration of light whispers of forces or phenomena lurking just beyond the edge of our models, waiting to reshape how we see the universe's grand architecture. Active galactic nuclei should be cosmic lighthouses, blazing beacons so bright they outshine entire galaxies. At their cores, supermassive black holes devour swirling disks of gas, converting stolen matter into torrents of radiation across the spectrum. Based on everything we know about physics, these monsters should be pumping out staggering amounts of infrared light as their blistering heat warms surrounding dust clouds. Yet when astronomers tally up the numbers, something's off. the cosmic infrared background contains far less light from a GN than simulations predict, as if these engine rooms of the universe are running on half power. This missing a GN contribution isn't just a bookkeeping error. It threatens to upend our understanding of how black holes shape their surroundings. Take the case of quasars, the most luminous AGN. Models suggest their infrared emission should dwarf their host galaxies, imprinting the CIB with unmistakable hotspots. But when researchers isolate quasar light in deep infrared surveys, their collective glow falls short by as much as 40%. Even stranger, the deficit isn't uniform. Some wavelengths, like those around 10 microns, show a steeper drop-off than others, hinting that the dust near these black holes might be cooler, sparser, or arranged in ways we've never seen. One explanation points to camouflage. Not all AGN announce their presence equally. Obscured black holes shrouded in thick cocoons of dust and gas could be redirecting their energy into longer wavelengths or even trapping it entirely. Imagine a spotlight buried under a mountain of soot, its glow dimmed and reddened, escaping only through narrow cracks. If the early universe hosted more of these cloaked monsters than we've accounted for, their hidden infrared output might be masquerading as ordinary galactic light. Recent observations from the James Webb Space Telescope lend credence to this idea, revealing candidate obscured AGN that traditional X-ray surveys missed. But there's a rival theory. Maybe the dust itself is behaving oddly. Near a supermassive black hole, radiation pressure should blast nearby dust grains to smithereens, leaving only a scorched zone where infrared emission is suppressed. Alternatively, the dust might be clumping into dense, unstable knots that intermittently block our view. Think of clouds passing in front of the sun, casting flickering shadows. Either scenario would skew our measurements, making AGN seem fainter than they truly are. The most unsettling possibility: we've misjudged the black hole's appetites. Standard models assume AGN feed continuously, like rivers flowing into bottomless pits. But what if they're more like intermittent geysers, gulping down matter in violent bursts separated by long fasts? During dormant phases, their infrared signatures would fade dramatically, creating gaps in the CIB that our snapshots in time might mistake for permanent absences. Supporting this, some simulations show that episodic feeding could slash a black hole's cumulative infrared output by half without violating other constraints. The implications ripple far beyond accounting for missing light. If AGN truly contribute less infrared than predicted, it could mean they played a smaller role in heating the early universe than we've assumed, potentially altering timelines for cosmic reionization or galaxy formation. Or perhaps we're glimpsing a new class of stealth black holes whose growth mechanisms defy our textbooks. Every unexplained photon in the CIB is a whisper from these cosmic titans, reminding us that even the brightest monsters in the universe still know how to hide. Dust shouldn't exist this early in the universe, at least not according to the textbooks. Conventional wisdom says it takes generations of stars to forge the heavy elements needed for dust grains to form. Stars burn hydrogen into helium, then forge carbon, oxygen, and silicon in their cores. When they die, they spew these elements into space where they clump into microscopic particles. That process should take time, yet the cosmic infrared background tells a different story, one where dust appears suspiciously soon after the Big Bang, like a magician pulling a rabbit from a hat before the audience has even settled into their seats. This early dust paradox starts with a simple observation. Certain patches of the CIB glow at wavelengths that unmistakably signal the presence of dust, but they correspond to epochs when the universe was less than 1 billion years old. That's barely enough time for the first stars to form, let alone explode and seed the cosmos with their ashes. To make matters worse, some of these dusty regions appear to predate even the earliest confirmed galaxies, floating in voids where star formation shouldn't have gained a foothold. It's as if the universe cheated, skipping steps in its own cosmic recipe book. one radical solution flips the script on stellar life cycles. What if the first stars didn't just die in supernova, they shattered? The most massive primordial stars, hundreds of times heavier than our Sun, might have met a bizarre fate known as pair instability supernova. These cataclysms don't just explode, they obliterate themselves so completely they leave no black hole behind, scattering their entire mass into space in a single, furious eruption. Such violent deaths could have flooded the early universe with dust in a cosmic blink, bypassing the need for slower, gentler enrichment over generations. But there's a catch. Even these stellar firestorms shouldn't produce dust in the quantities the CIB suggests unless the dust itself formed differently back then. Laboratory experiments hint that in the absence of heavier elements, hydrogen and helium might have combined into exotic, fluffy dust grains under extreme conditions. These fragile structures, unlike anything in today's universe, could have formed directly in the cooling ejecta of supernova, like snowflakes crystallizing in smoke. If true, the early cosmos might have been filled with temporary, otherworldly dust that later generations of stars replaced with the more familiar varieties we see today. Then there's the dark horse contender, black hole factories. Supermassive black holes already existed when the universe was astonishingly young, and their formation remains one of astrophysics' greatest mysteries. Some theories suggest they grew from direct collapses of primordial gas clouds, collapses so violent they could have forged dust in their turbulent outer layers like sparks flying from a forge. These black holes wouldn't just eat matter, they might have processed it, belting out jets laden with freshly minted dust grains that then drifted into the voids, imprinting the CIB with their ghostly signatures. The implications stretch far beyond accounting for a few infrared glows. If dust truly existed this early, it reshapes our understanding of how quickly the universe became chemically complex, and how soon the ingredients for planets, and perhaps even life, became available. Every anomalous flicker in the CIB is a challenge to the conventional timeline, a whisper that the cosmos might have been bustling with activity far sooner than we ever dared to imagine. The question isn't just where the dust came from, it's what else we've missed in our rush to map the universe's infancy. One of the most persistent headaches in studying the cosmic infrared background comes down to a simple question: when exactly is this light coming from? Pinpointing the eras responsible for the CIB's glow should be straightforward after all. The expansion of the universe stretches light to longer wavelengths over time, imprinting each epoch with a distinct redshift fingerprint. Yet when researchers analyze the data, they get wildly different answers. Some studies claim the bulk of the infrared background originates in the universe's rowdy teenage years, around 2 to 4 billion years after the Big Bang, when galaxies were forming stars at breakneck speeds. Others insist a significant fraction hails from much earlier, during the cosmic dawn's first tumultuous chapters. This discrepancy isn't just academic, it's a rift that could rewrite our timeline of how stars and galaxies lit up the cosmos. The heart of the debate lies in disentangling overlapping signals. Imagine listening to a symphony where every instrument's note has been slowed down by different amounts, blending into a discordant hum. That's essentially the challenge with the CIB. Light from galaxies at varying distances, and thus different epochs, gets smeared together into a composite fog. To tease them apart, astronomers rely on statistical cross-correlations, matching CIB patterns with galaxies of known redshift. But here's where things get messy. The same infrared fluctuations can plausibly align with both distant, ancient galaxies and closer, more modern ones, depending on the assumptions baked into the models. Take the Lyman break dropout technique, a common method for identifying early galaxies. By searching for objects that disappear at specific ultraviolet wavelengths absorbed by intervening hydrogen gas, scientists can estimate their redshift. When applied to CIB hotspots, some analyses suggest these regions correlate strongly with galaxies at redshift 6 or higher, meaning we're seeing light emitted when the universe was less than 1 billion years old. But critics point out that dust-obscured galaxies at lower redshifts can mimic the same spectral signatures, tricking us into overestimating the CIB's ancient contributions. Then there's the cosmic SED spectral energy distribution puzzle. Every galaxy's infrared glow follows a rough template based on its star formation rate and dust content. If you assume the CIB is dominated by galaxies like those we see today, its spectrum should peak at predictable wavelengths. Instead, it skews redder, as if laden with galaxies that are dustier, farther away, or both. Proponents of an early CIB argue this redness is a smoking gun for primordial galaxies, whose intense ultraviolet radiation got efficiently converted to infrared by surrounding dust. Skeptics counter that nearby, ultraluminous infrared galaxies, ULIRG, though rare, could be masquerading as a larger population of distant objects, their extraordinary dustiness amplifying their apparent redshift. The implications ripple far beyond chronology. If the CIB leans early, it suggests the universe's first galaxies were far more efficient at churning out stars and polluting space with dust than models predict. Alternatively, if the bulk comes from intermediate epochs, it might mean we've underestimated how long peak star formation persisted. There's even a third radical possibility, that the CIB's redshift mystery hints at unknown astrophysics, like exotic dust properties in the early universe or large-scale variations in cosmic expansion we've yet to account for. What makes this anomaly so compelling is how it exposes the limits of our cosmic archaeology. The infrared background isn't just a static relic, it's a palimpsest, its layers fused together by time and distance. Until we develop tools to peel them apart with certainty, the true story of when and how the universe switched on its lights will remain tantalizingly out of focus. Dark matter is supposed to be invisible, not just to our eyes, but to every wavelength of light. That's the whole point. It doesn't absorb, emit, or scatter radiation. It only whispers its presence through gravity's pull. Yet when scientists scrutinize certain anomalies in the cosmic infrared background, they catch glimpses of something peculiar. Faint, unexplained glows that align too neatly with the predicted distribution of dark matter to be coincidence. It's as if the universe's most elusive substance is leaving fingerprints in infrared light, fingerprints it shouldn't be able to make. This paradox has led researchers to revisit some of the wildest ideas in physics, including alternative forms of dark matter that do interact with light, just in ways we've barely begun to imagine. Take actions, for example. These hypothetical particles, originally conjured up to solve a quantum puzzle unrelated to dark matter, could theoretically decay into pairs of photons under specific conditions. If actions make up even a fraction of the universe's missing mass, their slow decay over billions of years might produce a faint infrared haze, concentrated along the dense filaments and halos where dark matter is known to cluster. The kicker, certain CIB anomalies, those unexplained excesses at precise wavelengths, match predictions for action decay signatures eerily well. But actions aren't the only dark horse in this race. Another contender is sterile neutrinos, heavier, sluggish cousins to the neutrinos we've already detected. Unlike their ordinary relatives, sterile neutrinos could decay into X-rays or infrared photons, leaving behind a subtle but measurable signal. Some researchers argue that certain CIB hotspots align too closely with the expected emission patterns of these particles, as if we're catching dark matter mid-transformation, shedding its invisibility cloak one photon at a time. Then there's the even more speculative notion of self-interacting dark matter. Most models assume dark matter particles pass through each other like ghosts, but what if they occasionally collide, creating bursts of energy? These interactions could heat surrounding gas or dust, imprinting the infrared background with telltale warm patches. It's a long shot, but if true, it would mean the CIB isn't just a backdrop. It's a live feed of dark matter's hidden choreography. Of course, skeptics abound. The biggest hurdle is distinguishing these signals from mundane astrophysics. Galactic dust, primordial black holes, or even overlooked populations of faint stars could mimic dark matter's infrared whispers. That's where cross-referencing comes in. By overlaying CIB maps with gravitational lensing surveys which trace dark matter's distribution via bent light, researchers can hunt for overlaps too precise to dismiss. A few tantalizing correlations have emerged, particularly in galaxy clusters where dark matter's gravity is strongest. Yet even these aren't conclusive, they're shadows flitting at the edge of detection. What makes this connection so electrifying isn't just the science, it's the philosophy. For decades, dark matter has been the ultimate cosmic placeholder, a blank check written to balance the books of gravity. But if these CIB anomalies hold up, they could transform dark matter from an abstract necessity into something tangible, something with physics we can probe. It's the difference between describing a stranger's silhouette and finally seeing their face. Until then, these infrared whispers remain the universe's most tantalizing maybes, hinting that even the darkest corners of the cosmos might still know how to glow. The universe loves pattern spirals in galaxies, branching veins in leaves, even the fractal repetition of coastlines viewed from space. But nothing prepares you for the cosmic infrared background's most mesmerizing quirk. Its glow isn't just patchy or clustered, it's recursive. Zoom in or out, and you'll find the same intricate textures repeating across scales, as if the universe scribbled its signature in infrared ink using a fractal pen. This self-similarity defies expectations. The CIB's light comes from eons of stellar births and deaths, black hole feasts, and dust-filled collisions, chaotic processes that should have left a messy, uneven fingerprint. Yet the deeper we look, the more its fluctuations echo themselves, whispering that there's order hiding in the cosmic chaos. What could sculpt such perfection? One leading theory points to gravity's slow-motion choreography. From the universe's first moments, dark matter's invisible fingers began kneading matter into a cosmic web, vast filaments intersecting at nodes where galaxies would later bloom. This web isn't random. It follows mathematical rules where structures at smaller scales mirror larger ones. If the CIB's glow traces this scaffold, its fractal patterns might simply reflect dark matter's underlying blueprint. But here's the catch. Simulations of this process almost match the CIB's recursion, but not quite. The real universe appears more fractal, more finely detailed, as if an extra ingredient amplified gravity's artistry. That missing piece could be primordial magnetism. Imagine the infant universe threaded with delicate magnetic fields, woven during inflation like invisible spider silk. As galaxies formed, these fields might have guided gas flows with extra precision, sharpening the fractal edges of the cosmic web. Supporting this, some CIB anomalies align with rare regions where ancient magnetic imprints were caught fossilized in galaxy clusters, like cosmic pressed flowers preserving a lost era's secrets. Yet critics argue that magnetism alone can't explain the pattern's sheer uniformity. The fractalness persists even where magnetic influence should have frayed, suggesting something else is at play. Then there's the radical fringe, non-Euclidean spacetime. What if the universe's fabric itself has subtle folds or creases at colossal scales, warping how light accumulates across billions of years? In such a cosmos, the CIB's fractal glow wouldn't trace matter's distribution, it would map the shape of spacetime's hidden geometry. Think of it like light filtering through frosted glass. The pattern on the other side reflects the glass's texture, not the light source. This idea borders on heresy, since Einstein's relativity assumes spacetime is smooth at large scales. But if the CIB's recursion holds up under sharper scrutiny, it might force us to reconsider whether space itself has a grain. Of course, there's always the skeptic's refuge, coincidence. Fractals emerge everywhere in nature, from fern fronds to lightning bolts, because simple rules often breed complex repetition. Maybe the CIB's patterns are just gravity's default output, no exotic physics required. But that's the thrill of this anomaly. It sits at the crossroads of the known and the unimaginable, daring us to decide whether we're seeing the universe's effortless symmetry or the first cracks in our understanding of how structure unfolds. Every recursive flicker is a question written in light, asking, does the cosmos play by rules we've yet to decode? The cosmic infrared background shouldn't be a time traveler, yet in certain wavelengths it behaves like one. Imagine flipping through a family photo album and finding the same face in pictures taken decades apart, unchanged, as if the person existed simultaneously in multiple eras. That's the essence of Anomaly 39, emissions at specific infrared wavelengths that appear to originate from wildly different cosmic epochs, overlapping in a way that defies the linear flow of time. These signals shouldn't coexist, like finding a medieval castle lit by electric lamps. At the heart of the puzzle are spectral lines, distinct wavelengths where dust, gas, or molecules emit or absorb light. When astronomers analyze the CIB, they expect each line to tell a clear story. Shorter wavelengths correspond to more recent sources, while longer, redshifted ones point to the ancient universe. But in scattered patches of the infrared sky, those rules break down. For instance, the emission line for polycyclic aromatic hydrocarbons, carbon-based molecules that glow at 7.7 microns, shows up alongside its redshifted counterpart from much earlier times, as if the same chemical fingerprint was stamped across billions of years. It's like hearing a modern pop song and a Gregorian chant playing in perfect unison, despite being separated by centuries. One explanation dances on the edge of astrophysical heresy: contamination. Could nearby interstellar dust, reflecting or reprocessing light from modern stars, mimic the signatures of primordial sources? Some researchers argue that delicate photon scattering where shorter wavelength light gets absorbed and re-emitted at longer wavelengths might blur the timeline artificially. But this fails to explain why the overlapping emissions cluster in specific regions rather than scattering randomly. If contamination were the culprit, the effect should smear uniformly, like ink bleeding through paper, not gather in deliberate knots. A more provocative theory involves cosmic recycling. Picture a massive galaxy in the early universe, spewing dust and metals from supernova into its surroundings. Fast forward billions of years, and a new generation of stars forms from that same recycled material, inheriting nearly identical chemical compositions. When their infrared light reaches us, the spectral lines from both eras could align almost perfectly, creating the illusion of temporal overlap. It's a compelling idea, except that the chemistry of star-forming regions evolves over time, meaning even recycled material should show subtle differences. The CIB's overlapping emissions, by contrast, match too precisely, like two fingerprints belonging to the same person but lifted from different crime scenes decades apart. Then there's the wild card: light's journey through warped space-time. General relativity tells us massive objects can bend light like a lens, but could extreme gravitational distortions, say, near a supermassive black hole or a cosmic string, stretch and fold infrared emissions in ways that mix signals from different epochs? Simulations show that under rare conditions, time-delayed lensing might superimpose light from ancient and modern sources along the same line of sight, like a funhouse mirror reflecting multiple eras at once. The catch: these scenarios require such precise alignments of mass and perspective that they should be vanishingly rare, yet the overlaps appear frequently enough to demand attention. What makes this anomaly so unsettling isn't just the scientific contradiction, it's the philosophical ripple. If light from disparate eras can blur together so seamlessly, how do we trust any timeline written in the cosmos's glow? The overlapping emissions force us to question whether we've misread the universe's history, or if the infrared sky is subtly rewriting the rules of how we measure time itself. Until we untangle this knot, every anomalous wavelength remains both a clue and a warning. The past might not be as distant as we think. The cosmic infrared background's 40 most baffling anomalies might not stay mysterious for long. A new generation of telescopes armed with unprecedented sensitivity and cutting-edge technology is poised to peel back the veil on these cosmic riddles, transforming whispers in the dark into clear, actionable data. Leading the charge is the James Webb Space Telescope, JWST, already revolutionizing infrared astronomy with its ability to peer back to the universe's first galaxies. But JWST is just the beginning. Missions like SPHEREX, NASA's upcoming all-sky infrared surveyor, will map the entire sky in 96 different wavelengths, creating a cosmic fingerprint database that could finally link CIB anomalies to their sources. Imagine trying to solve a jigsaw puzzle with half the pieces missing until now. These instruments are handing us the remaining pieces, and the picture they reveal might rewrite astrophysics. SPHEREX's unique strength lies in its spectral precision. While JWST zooms in on individual targets like a cosmic microscope, SPHEREX operates as a wide-angle lens, capturing the infrared sky in exquisite detail. This sweeping approach is perfect for hunting down the faint, diffuse signals that make up the CIB, especially those odd fluctuations and spectral bumps that resist explanation. By cross-referencing its findings with JWST deep field observations, astronomers could pinpoint whether those mysterious infrared excesses come from primordial stars, dark matter decay, or something entirely unforeseen. It's like combining a detective's notebook with satellite surveillance. The clues are there, and soon we'll know where they lead. Then there's the European Space Agency's Euclid mission, designed to map the dark universe with blistering precision. While its primary focus is dark matter and dark energy, Euclid's infrared eyes will also scrutinize the CIB's large-scale anisotropies, testing whether they truly align with the cosmic web's hidden scaffolding. If Euclid finds that CIB hotspots trace dark matter filaments too neatly to be coincidence, it could solidify the connection between the universe's visible and invisible architecture. Even more tantalizing is Japan's upcoming SPECA mission, a far-infrared observatory that will study cold dust and molecular gas with unmatched clarity. SPECA could crack the case of the too hot early dust paradox, revealing whether exotic physics or overlooked astrophysical processes were at play in the universe's infancy. But the real game-changer might come from the proposed Origin Space Telescope, a concept for a far-infrared observatory with 50 times the sensitivity of any predecessor. Origins could detect the faintest infrared whispers from the cosmic dawn, potentially catching population 3 stars in the act of igniting, or spotting the infrared echoes of dark matter particles annihilating in deep space. With capabilities like these, the CIB's enigmas won't just be studied, they'll be dissected, each wavelength a thread leading back to the universe's most formative moments. What makes this era so electrifying isn't just the technology, it's the questions we're finally equipped to answer. Are primordial black holes lurking in the CIB's unresolved light? Does the infrared dipole hint at a universe far less uniform than we thought? The next decade of observations won't just fill gaps in our knowledge, it could tear those gaps wide open, revealing a cosmos stranger and more dynamic than we've dared to imagine. The cosmic infrared background has been patient, holding its secrets for billions of years. Soon, it won't have a choice but to give them up. From ghostly dark galaxies to unexplained infrared echoes of black hole collisions, these 40 anomalies aren't just isolated puzzles, they're pieces of a far larger mystery, challenging the very foundations of how we understand the cosmos. Each one defies expectations in its own way, the missing light that refuses to add up, the dust that shouldn't exist so early, the fractal patterns that hint at forces we've yet to name. Together, they paint a picture of a universe far stranger and more dynamic than our textbooks ever predicted. These aren't minor gaps in knowledge. They're seismic cracks in the framework of astrophysics, suggesting that somewhere between our models and reality, there's a disconnect waiting to be bridged. Maybe it's dark matter behaving in ways we never anticipated, or the first stars burning brighter and dying faster than we thought possible. Perhaps it's something even more profound, a fundamental law of nature we've yet to uncover, hidden in the infrared glow of the cosmic background. But here's the thrilling part. Every anomaly is also an invitation. With tools like the James Webb Space Telescope and future missions like SphereX, we're on the verge of turning these cosmic whispers into answers. The next decade could rewrite our understanding of the universe's infancy, its structure, even the nature of dark matter itself. So stay curious. The cosmos is still writing its story, and these 40 anomalies are just the cliffhangers. The next chapter, that's for us to discover.